Hello. So it's going to be a 12-hour stream. Is it? Oh shit, it's flipped. I need to flip it. Flip it. Flip, 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 horizontal. Oh, hey. Now it's back to normal. So I need to check my mic. Mic. Pa. Should be in my subscription, right? Ah, my neck. My neck hurts. Do I follow myself? I should. I should follow myself because I'm really smart. Because God gave me divine intellect. Ah, okay. I don't follow myself. I should though. What do you mean I don't follow myself? Subscribe, of course. Ah, the fuck? What the fuck is this quality, bro? Okay, I don't follow myself. I should though. What do you mean I don't follow myself? Subscribe, of course. The Bro, some of the numbers have been skewed. It's crazy. No, 82, whatever. Okay. Why is my bro? What happened? What happened to this shit? It's crazy. Why am I screaming in the most dog shit? Whatever, bro. Why am I screaming in this? I got the mic. What is it? Is it the? Is my last stream this way too? No way. In this. I got the mic. What is it? Is it the? Bro, it is. What the fuck? No way. I've been streaming. I've been streaming in this quality. No way. No way. What the fuck? Why am I streaming in the lowest quality possible? I don't know. Okay, anyway, this is a diary for myself more than any. So today, you know what I should do? I should like write like a summary on the comment section every day on like what I've done on the stream. I think that is much more valuable than not writing it out. Okay. Let's try something. It's kind of hot here, weirdly. Writing it out. Okay. Let's try something. It's kind of hot here, weirdly. Okay, you guys don't hear it. My mic is kind of good. What do you study? Like, what can you like study? I don't know. Let's do. I need to do. Okay, let's do the rotated arrays, which I need to do anyway. Ooh, should I do this? Probably not. Rotated arrays. I don't really get that question though. Rotated arrays. Did I misspell it? Brother. When is it? Like, what the fucking hell? Uh, okay, let's close this tab. I don't really need it. Let's go here. DSA. Bro, not papers. DSA. Let's go. I wanna Um. Yeah. Fuck you. I wanna fucking beat the fuck out of you. Okay. Let's go here. Let's pray to God. Okay, let's do this.
Hey guys, Greg here. Let's solve 153, which is find minimum in rotated sorted array. So suppose an array of length n is sorted in ascending order, so the numbers are going up, but then it's been rotated between 1 and n times. So for example, the array of originally nums as just the numbers 0 to 7, if you rotate...
Wait, have I done this before? I'm pretty sure I did this, right? It's just like basic, yeah, I did this. It's using a binary search. Fucking hell. Fucking hell, mate. Bro, just show me the merge sorted array. Sorted array of a square. Okay, can you just, what's the number? 153, 153? 153, because I've not even attempted it, no way. So I did something similar the other day. Don't know which one it is. One of pow. Search a 2D matrix. Yeah, I think I did this one by myself. Just fucking awesome. I should be. Coco eating a banana. Wait, this is to find the minimum. Yeah, let's. So how do I do it with binary? Yeah, bro, it was like something with the graphs coming in and shit like that. That's like too complicated. No way I'm doing that. Okay.
4 times, that would become 4 to 7, and then 0 to 2. Why is that? Well, if you track the 4, for example, all the numbers are going to follow suit. So tracking the 4 here, it's going to move forward, and if it goes to the end, it's going to wrap around to the beginning. It's going to go forward 4 times. So the 4 starts here, it moves forward once, twice, 3 times, 4 times, and all the other numbers will follow suit. So it starts at 4, it's going to go up until 7. There's going to be this critical point here where you go from increasing just to decreasing in one step. There's only going to be one spot where that's true because it's increasing in general, but because we've now rotated it, there's this pivot point where right here it goes from increasing order just to decreasing one step here, and your minimum will be on the right side of that, and then it goes to increasing again. And here, this is the only circumstance where it is just increasing up. Okay, so you have the chance of this pivot point, but also it could be the case where it's just original sorted order as well. So we're given the sorted rotated array nums of unique elements. Okay, let's unpack that because that's actually a lot. We are given the sorted rotated version. So this has already been rotated. We're not given like the amount of times that it's been rotated or whatever. We've just been given this rotated array and we need to return the minimum element of the array. And also they are all unique elements, so there's no duplicates. Given that thing, we have to return the minimum element of the array. So that's going to be either that first value there if it's fully sorted, or it'll be that one just after that pivot point. Now, furthermore, we actually need to run an algorithm that runs in O of log n time. And if you've done a binary search problem or two, then this should be screaming binary search to you as something to try. Okay, so let's just look at one of these examples here. This should be enough. So 3, 4, 5, 1, 2 is our input. The output is 1 because that is the value, not the index, but the actual value of the minimum element. And the explanation is that the original array 1, 2, 3, 4, 5 was rotated 3 times. That's kind of a misleading explanation. It's correct and that's not invalid. It's just that we actually don't even really care. Like that, the fact that this is true isn't even important to us for solving the problem. Now, if you haven't heard of binary search before, I would check out my video on that. We actually have a couple of them on here already. It's just that we actually don't even really care. Like that, the fact that this is true isn't even important to us for solving the problem. Now, if you haven't heard of binary search before, I would check out my video on that. We actually have a couple of them on here already. So we're going to start off with just pretending we can do a binary search here. I know that's kind of problematic because we have this version in the middle here where it's not sorted, but let's just give this a try and try to tweak it. So we start L at the first index and R at the last index. Now for a binary search, you would calculate your middle index, which is going to end up being here. You can do that through the formula L plus R over 2. That means integer division. Okay, so that'll get you your middle index, but just drawing it, it's going to be right here. And of course, we can access this value here. So we have 3 values of interest, 4, 7, and 2. Now in normal binary search, you'd expect this value to be higher than this value. We'd actually just kind of guarantee that that's true, but we can't in this case. We want to try and discover this pivot point. Okay, if we can find this over here, then this actually gets really simple. The problem is that this value may or may not be bigger than this. Now let's actually just forget about the left for now. It turns out to not matter as much. So we have the middle value of 7, and we need to actually compare that to what's on the right. Now, if it is bigger, if this value is bigger, what does that mean? Let's actually just pretend it was over here for a second. So if the middle was here and the right was here, well, we discover that the middle is greater than the right. And I mean the values, not the indices. So the middle value is bigger than what's on the right. Well, it means that M is in this situation over here, where if the middle is bigger than the right, it means that the pivot point must be somewhere over here. Okay, the pivot point must be in this range. Why is that true? Well, if the middle value is bigger than what's on the right, well, that means there must be some point where we actually went up, 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 and then we hit the bottom. If the middle value is bigger than what's on the right, well, that means that over here somewhere, strictly to the right side of M, that pivot point, which we know is here, that must be to the right of M. Okay, so say if we found that's true, let's actually write this down as a rule. And again, I mean the values of M and R, not the indices themselves. So if M is greater than R, the rule is that the pivot point is somewhere to the right. What does that mean? Well, we need to update our bounds. It means we want to set L to equal M plus 1. So we set L to be M plus 1 because now, what do we see? We're looking in a better range here. We know we don't care about the pivot points over here. It must be now somewhere in this range. So we're just going to keep asking this question. What if the case that this is not true, as in M is less than or equal to R? Let me just make this a little bit smaller because that seems to be taking up all the space here. So let's get our new middle value. We'll get M, and let's write the math out this time. So this is index 0, 1, 2. So M we know is equal to L plus R over 2 integer division. That is going to be 3 plus 6, and then integer division by 2. That is going to give 9 over 2, which rounds down to 4. 4.5 rounded down is 4. So we are going to get M as this element right here. Okay, so now we actually need to figure out what we want to do if M is less than R. Okay, so we're not in this situation. We're in the else. Could this be the minimum? Okay, could M actually be the minimum? So in the case that M is less than R, this actually could be our minimum value. And it turns out that it is. But we need to keep looking in the correct range. So what do? We want to narrow in on this minimum. So if M could be that minimum and we want to get closer to it, we set R equal to M. Why can we get rid of all of this range here? Well, we know that this value is smaller than over here, and therefore we're looking for the smallest value. We want to update our range so that we get rid of these bigger values and narrow down in on this minimum. So in the case that M is less than or equal to R, we actually want R to equal M. That gets rid of that right side range, and we move down to narrow in on the minimum. Okay, let's do this one more time. We'll get our middle value is 3 plus 4 divided by 2 integer division. That's going to round down to 3. So our middle value is going to be right here. We ask the question, is the value at M greater than R? If this value is greater than over here, well, we know that the minimum is going to be strictly to the right over here. And so what do? Well, we follow our same rule. We set L to equal M plus 1. At this point, we can see that we have R and L are equal to each other. And that is actually when we complete this loop, because we're going to end up doing this while L is less than R. When they're equal to each other, we break out, and that is when we're on the minimum. So notice that following these sets of rules right here, following those rules, we will narrow in on the minimum. Okay, with that being said, let's write our code. So we set n equal to the length of the numbers. So we can start our binary search with L is equal to 0 and R is equal to the last index, which is n minus 1. Now we want to run this, as we said, while L is less than R. So when they're equal to each other, we want to escape. And actually both L and R are located at the minimum. We get our middle value, which is L plus R into integer division by 2 to get the middle index, and then we just keep asking the question, hey, if nums at at m is actually greater. Could m be the minimum? guess it actually could, but we want to get closer to it, and so r we set equal to m. We don't want to lose track of the minimum, so we don't go past it. We set r equal to m. After we escape here, we could do either nums at L or nums at R, because we're escaping when L and R equal to each other, so we'll run that, and as you can see, that is going to work. So for the time and space complexity here, well, the time
Please, can you work? Doesn't even work. If you can hear me. Okay. Fuck. It's gonna. It's pissing me off, man. These in like what the fuck? I can't do that. I can't do that. Like what the hell? It's a disgrace, bro. It's a disgrace. How do I fix my audio? Desktop audio. Shuka. Check. Holy shit. Ah, my neck. My neck. It hurts. Droid. Okay.
Okay.
Fine.
Fine. You got me now. Hopefully you guys can hear me. Whew. The shit that you have to do today, man. It's crazy. So this is how you do it for the lower bound. It's the upper bound method. Should I get Claude? Claude. This will be a lower bound. We're using the bro, it's not even fun. Upper bound. We'll be using the. So what's the difference, lower bound versus upper bound in binary search? Doesn't even matter, I think.
I want to find the index of 2, but such that it is the last 2. So maybe that might be index 4. Because this 2, it's the very last one. And
Brother, what the fuck is this? Are you like stupid, brother? Find the minimum of this problem. You're given in a rotated sorted array. Find the minimum element. Okay. The array was originally sorted in ascending order, then rotated at some pivot. This approach finds lower bound in rotated point. First element is smaller than the last element. Okay. Compare nums mid. Okay, if nums mid is bigger than this, okay, we're not even doing that. If it's not rotated, okay, we're done with that. We're comparing nums mid to the right because it is the lower bound method. This will be the upper bound. Which one to use? situation, lower bound versus upper bound. I don't think, let's look at this. Different perspective, nigga, like I don't need a different perspective. So lower bound and upper bound implementation.
The video of Star Wars A to the DSA code. Welcome back to
Bro, you haven't even, what the fuck? Like, these guys haven't even, like, done their reps, man. They want to teach you. Fucking punks. Podcasts. Traditional coding days. No, bro. Let's see.
Hey guys, Greg here. Today I want
Conditional time and space complexity, the code.
Okay, so it's false. Make it not false. It is
Let's look at this. Whew. Bro, it's not that deep. Not that deep, bro. Bro, they Anthropic, they wrote a fucking, bro, they wrote an entire program. Kidding me. Control T, I think. Fuck, Control T is not the one. Control T is terminate. Oh shit, is it? Lower bound gives you the minimum resource in any algorithm needs to in the worst case. In the problem of comparison, no solution beats upper bound. Beats this upper bound O shows the maximum resource in a specific algorithm. No, in binary search.
information we have right here. Well, we don't.
Like, I don't even understand what I'm trying to say. Lower bound. My neck.
All right, what's up everyone? We are live here. So today what I want to talk about is the 3 levels of binary search. And specifically what I want to do is I want to dig into some of the applications of binary search and some of the ways that you might use it in an interview. They're not typical. Most of the time, we use binary search in a very basic way, right? We have an array and we want to find all the values in the array. But there are a couple ways in which we can use binary search and a couple levels at which we can use it that are more involved and that allow us to solve all sorts of other problems that don't actually look like binary search problems. So in this training, I want to go through what are some of these ways that we can approach problems using binary search. So let's go ahead and dig into it. And the first thing that we're going to do is make sure that we're all on the same page here with what binary search actually is and how that works. Because
yeah, bro, he does look like a... Yeah. I'm really stoked to like give you all of my money. Stranger on the internet. I'm really stoked, actually.
if we don't have that fundamental binary search, then it doesn't matter if we try to do all these other things because we don't know how to do it, right? So if we have...
Hello and welcome. I'm James Murphy, and today we're talking about binary search. Binary search, also called bisection search, is an algorithm for finding an element quickly in a
Oh, whoa, pause. I ain't like that. Okay?
sorted array. Suppose we're trying to find 7 in this array. Is it in the left half or the right half? The right half, and then repeat. Finally, there's just one element left. That's our 7. Even though it's one of the first algorithms that one learns, it's also extremely important. Analyzing binary search is often the branching point for studying things like time complexities of algorithms and big O notation. Here you can see we started with 8 elements, and at each step we ruled out half of them. This idea of ruling out half of all the possibilities at each step is where binary search or bisection search gets its name. This is also where it gets its logarithmic time complexity from. So binary search is useful, fundamental, and simple. And yet, a huge percentage of programmers, even professional programmers, struggle to write binary search. How can the idea be so simple, but the implementation be so difficult? Well, it's not so difficult. You just have to think about it in the right way. The first thing we should decide on is, are we returning the object that we find or the index that it was at? The index itself is a more useful piece of information. We can always just grab the object at that index later. But what do we do if the object we're looking for isn't there? Do we do something like return -1 or maybe raise an exception? Or what if there are multiple valid indices to choose from? With every arbitrary choice that we make, we would have to remember the implementation details that go with that choice. A better way to do it is to rephrase the question so that there's always exactly one answer. So here's how I would rephrase the question. If I were going to add another 7 into this sorted array, where should I put it so that it's the first 7? Notice that in this hypothetical, I'm always adding the 7 into the array. That guarantees the array is not empty and always contains at least one 7. But if it contains at least one 7, then there is always a unique first 7. The index of that first 7 is the answer to my question. It doesn't matter whether or not the original array had a 7 or multiple 7s in it. The location of the first 7 in the new array is always uniquely determined. If there were no 7s, I would have to put it here to maintain the sorting property, and if there are already 7s, it would have to be the index of the first already existing one. Even if the array were empty, I still get a valid answer. In this case, I would have to insert the 7 at index 0. Notice that 0 is not a valid index into this array, but it still makes sense because the question that I asked was, where should I insert it? And it certainly makes sense to insert it at index 0. The same applies for a non-empty array. Binary search might tell me that I have to put it at the end. As long as you keep in mind this interpretation of what binary search is supposed to return, it's much harder to get confused. I think that far too often, binary search is taught solely as an algorithm that works on sorted arrays. But the array being sorted, I claim, is not actually the property that we're using here. Here, look, I changed some of the elements, and this array is no longer in sorted order. But notice, the steps are exactly the same. What we need is that everything less than 7 is on the left and everything bigger than 7 is on the right. In this array, the numbers have been replaced with the important information. Is this number less than 7? Notice how any trues are on the left and any falses are on the right. So now that we're looking at the relevant data, where do we insert 7 so that it is the first 7? Notice that the answer that we're looking for is the index of the first false value, or the end of the array if there are no false values. This is the key insight that we need to keep in mind that makes the implementation extremely easy to remember. Squint your eyes and find the first false value. Okay, let's write the implementation. Low and high are lower and upper bounds on midpoint.
Bro, low and high.
Low
Don't left and right. None of this low and high bullshit.
plus half the distance between low and high. If you write it this way, it will never overflow. It gives the right answer. Well, we know.
Yeah, this shit like. Oh wait, is that like a thing? No way. Aim, aim, will it work? No? Yeah, needs to be certain. Then it's like out of the index, then it becomes, yeah. This becomes out of the index. Obviously, this guy isn't using it.
Know that low is always less than or equal to, the
Oh,
correct
that's
answer is always
stupid.
less than or equal to high.
Kind of stupid to mention that. Lower bound, yes, inserting inserted lower bound and upper bound are variants that pinpoint the insertion points and ratio of duplicates. Return the first position. Why use what? Okay, how lower bound is different from enunciate. When to use upper bound, that's for duplicates. Use lower bound to find the first occurrence of a value. Okay, lower bound to find the first occurrence. Use upper bound to find the position of the last occurrence. Okay, that's a interesting tidbit. So 1, 2, 3, 4, 5. Fucking hell. It's horrible, mate. Horrible. 1, 2, 3, 4, 5, 6, 7. So I'm using lower bound to find, let's say it's 5, to find in duplicates. I don't care about duplicates, bro. I don't want to do this like fucking tidbit bullshit. Use lower bound. Okay. Goal. Okay, beautiful. So exist. If this exists, first match, I need to use lower bound. All matches and ranges and count. Okay, I can use both. I think lower bound is better. Which is better? I think it's lower bound is better, isn't it? After last match, strict versus target. What does it even mean? Strict versus target. Yeah, it's a lower bound way of doing it. It's an upper bound way of doing it. Lower bound binary search. This is the upper bound. I think so. Yeah. Custom binary search variants serve as a main alternative to ST lower bound to find the last occurrence in the sorted array for duplicates. Fucking who cares? What even is this? Bumbleclad, bro. Don't show me some bumbleclad bullshit. Okay. What's the number?
Let's write some more names.
1 5. Supposed to be hard. Okay, 1 5. You 1 5 3. I don't think I did it. So 1 5 3. No, 1 5 3. And sha la 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 la, sha la 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 la, sha la la la, sha la la la. Okay, search and rotated. Alright, I think it's the same thing. So I'm given it was 4 times rotated. How many times in L logarithm of times? Okay, so left is equal to 0, right is equal to length of nums minus 1, the last of. Okay, I'm using okay, how many times it needs to be rotated? So 1 2 3 4. Okay, I just need to return the length. I just need to return L. Wow. Okay, so middle is gonna do. I'm gonna do this. I don't want to memorize it. L minus. What even is that, bro? You gotta minus it in like a weird way. Fucking this. No. No, another fucking retard way. Why are you not using that? The fuck? Whatever. Maybe it doesn't overflow this time. Who knows? Who knows? We're just learning all along the way, like the rest of the world. You know, okay. M is equal to that, so we're gonna check if nums of. We're gonna use the lower bound because I don't know why I should use one thing over the other. I need to use ChatGPT the next time. So M, if the middle value of M is bigger than the lower bound, it will be the R. Okay. What? So this is the middle value, and it tests this value is bigger. So I need to check if that is bigger, how many times it needs to be rotated. I need to, if that is bigger, it can't be bigger. That's the whole point. Okay. I need to switch. What is equal to M? Return L. That's it. Fucking hell, bro. How am I supposed to do this? Okay. Needs to be rotated 4 times, and it's stuck in 2. Not even 2. It's stuck in here. -1 expected output. What the fuck? Should I return -1? Does it say within the number? Return the index of a target within if it is not present. Bro, I thought it was sorted array. What the fuck? Okay, they're giving me a target too. Okay. Fuck, that changes everything. So this needs to be in the first place. 4 needs to be important. What? So you have the left, right. That's the bound thing, upper bound thing. Divided by 2. I need to do the upper bound. How do you even do that? I don't know. God will do it. God will do it. You already know God will do it, right? God will do that. My God could do anything. This thing right there. It's fucking retarded and stupid. I don't even know why it is a thing. What's up with it again? If target, okay, it is in 3, returning -1. Okay. So we're using that. Let's run this. So my target should be 0 and it's 1 because we're incrementing. So this runs. So this should be no. No. One, two, three. Okay, 1, 2. I don't have to like rotate it at all. So what is the solution? Bro, I don't want to do this. This is too big. It's a 2-pass. What even is 2-pass? Binary search. Yeah, it's too big, bro. If it's too big, I'm not doing it. Personal choice. I'm not doing it. Too big, I ain't doing it, bro. Search rotated. So it's not even sorted though. The fuck is this sorted? 0, 1, 2, 3, and I'm supposed to find 4. The 4 is not in here, and the target is 1. I need to rotate it 4 times and I return L. Like, what am I supposed to do? Like, but this is the previous code. Fine, which is pretty good. I'm not gonna complain. Yeah, it's identical, isn't it? It's identical.
Hey guys, Greg here.
Always, bro. Always go for the smart one.
Hey guys, Greg here. Let's solve LeetCode 33, which is search in rotated sorted array. Now, firstly, if you haven't solved the problem, find minimum in rotated sorted array, you should definitely do that first, and I have a video on that. If you have,
So this is minimum, right? Okay.
then here we are. So behind the scenes, imagine this array was actually sorted first. So it was 0, 1, 2, 4, 5, 6, 7. It's now been rotated, which means all the values have been shifted over, and if they ever go out of bounds, they go to the back here. So this array was actually rotated 1, 2, 3, 4 times. 0 should originally be at the beginning, so it's been rotated 4 times over to get to the right, and so it's now 4, 5, 6, 7, 0, 1, 2. So you can find the minimum value here with kind of a clever binary search, and that's covered in other video, although we'll have to cover it a little bit again here. So you can find that minimum value here, and that was the solution or the end to the other problem. That's basically the beginning of this problem. After we've located this pivot index here, or the minimum, you actually have a target to find. So we are looking for the index of where 0 is, and if you can't find it, that's when you return -1. Okay, so let's solve the same example. These are the same number. Parking first, that's not this one. So really, I'm just going to count this as kind of an edge case here. Our target, it doesn't even really matter what it is in this case, because this is perfect range for binary search. You can just search for any value here, and it's particular where this comes. And then we'll run while strictly to the right side. We want L, we'll get our min index is either L or R, and so we'll just store that the min index, which I'm calling min I, that is equal to L, or R would also work. Now we need to do another binary search, knowing that we have this spot where it pivots. So we need to set up our bounds for our binary search, which is again just going to overwrite our L and R. If it's true that the min index is equal to 0, that is the edge case where we just want to run a normal binary search. So we just set L and R to be 0 and n minus 1. Okay, so if that's not the case, then we have our more complicated situation. So we want to say otherwise if it's true that the target is at least nums at 0, so if it's at least the first value, and the target is actually at most the maximum value, so if it's less than or equal to nums at min I minus 1. Okay, so this is basically checking if it's in the left partition. If it is, then we want L and R to be, well, we want L to be 0, and we want R to be the maximum, which is min I minus 1, or the index of the maximum. Otherwise, if that's not the case, it's got to be in the right partition, so we will set up our bounds so that L is going to be inclusive at the minimum index, and we want R to be up until the end of the array. Then from here, we're just going to write a traditional binary search. There's really nothing new here. While L is less than or equal to R, we need the equal sign here because we want to check if it's that value when L and R are equal to each other. So while L is less than or equal to R, we get our middle index, which is equal to, as usual, L plus R over 2. We say, hey, if the nums at the middle index is actually equal to our target, well, that means that we found it and we can return, well, in this case, we want to return the index for the problem, so we return M itself. Otherwise, let's check if nums at M is less than the target. If that's true, our target is to the right of our middle. We need to update our left bounds.
Nah, I don't think this is optimal. So L is equal to 0. What do I need to do? If we're doing the lower bound method, which is this one, if middle is bigger than this value, the last value, I need to basically, yeah, I need to like switch the left pointer to the middle pointer. So else I need to go right into, so then when it transgresses, when the right pointer becomes bigger than the left pointer, the loop exits, and I'm gonna just return the index, the value, which is the left pointer. which is placed on. Which it is placed on. Okay. Let's submit. It beats 100%. Cool. Easy solution. Fucking pussy ass bitch. Bro, I don't want to do this. What the fuck? Respectfully, no. Respectfully, dog, I ain't doing it, dog. Okay, this looks easy. We're doing, is it, I don't want to do it. This left partition doing a I don't know. It's just like garbage, neat code. Bullshit. Bro, I remember seeing one of the worst solution. I remember it. I forgot which one it is. I remember like seeing one of the worst solution on this section, and it has like a couple of thousand likes on it. So funny.
We want to go.
It was like some basic easy question, and the dude has like 100-line code. It's like a C++ code too, so I couldn't understand shit. It's so funny.
Past the middle index because it wasn't the middle index, so L is equal to M plus 1 in this case, and then otherwise.
Bro, what? Bro, I ain't doing it, bro. I ain't doing it, bro. Give or take, it's gotta be like 5 seconds. Why is it needlessly complicated? I feel like the solution that I came up with is like pretty good. But it's like, what the fuck is this edge case? Know what I mean? So just to fix. Analyzing your code. Doop. Fucking idiot. Bro, what I did right there, it's fucking genius. So if I can't find it, I'm just gonna return it -1. Bro, this is a perfect code. I don't see why it is wrong. Why is it wrong? Genuine question. Why is it wrong? It's one of the best codes that I've seen. Word to God, mashallah. What's going on?
Okay, let's solve LeetCode 33 search and rotated. Sure, since we're in the left sorted right sorted portion of the rotation code value. So we can eliminate all of these. We can cross out our middle and left. When you're doing binary search, and it's possible we can say it's greater than the left, so we can just.
But I genuinely don't understand that question. It's 33.
Hello, and welcome back to the Cracking Fan YouTube channel. Today we're going to be solving LeetCode problem 33 through our edge cases.
Bro, it looks ugly, man. Just learn how to draw, please.
Welcome to LeetCode Line 375. We'll be solving the top 75 LeetCode questions. This problem's search in rotated sorted array. Welcome to LeetCode Line 375. We'll be solving the top 75 LeetCode questions. This problem's search in rotated sorted array. Suppose an array sorted in ascending order is rotated at some pivot point. Say we're given a list like this, 0, 1, 2, 4, 5, 6, 7, and it can be rotated in this format, 4, 5, 6, 7, 0, 1, 2. So it's still sorted, sort of, but it's spliced at a certain pivot point. We're given a target value to search, and if that array is found, return its index, its actual index, or otherwise return -1. Okay, so here's our approach. Why don't we do a binary search and first find that pivot point? Here in this example, the pivot point is going to be what? 4, right? 0, 1, 2, 3, 4, no, it's 4. Because that's the point where the actual sortedness of the array exists. Once we find that pivot point, we can just do a regular binary search and return the actual index. So let's first initialize some variables, get the length of nums, as well as the left and right pointer. Now, while L is less than R, we're going to check, first calculate the midpoint and say
the fuck is
L
this?
plus R divided by 2. If the nums midpoint is greater than nums to the right, that means that this pivot point must exist on the right side. So if that's the case, we'll just make left equal to mid plus 1. Otherwise, we'll move our right pointer equal to mid. And the reason we do it like this is at a certain point, it's going to point to these 2 pointers, and we want the left pointer to move to the right, because we want the index number right where the pivot point starts. So now that both the left and right pointer is going to be pointing to the pivot point, we can just initialize the pivot, just make it a little easier here. And now we'll do a regular binary search. So while L is less than or equal to R, we'll say first calculator
N, capital N. What the hell?
midpoint.
So, bro, we're doing another binary search between the pivots, between 0, 1, 7, and 0. What?
And here's the thing, we need to calculate the real midpoint using our pivot. So all that is just to add the pivot number, and we need to do a modular by the length of the array. And that's going to give us the actual number that we were pointing at, even though this binary search pretends like this is just a regular sorted array. So if nums.mid2, if that equals the target, then return mid2, which is the actual index. Otherwise, if nums mid2, if it's what? Less than the target, what do we want? If this point is less than the target, then we know we need to move to the right side, right? So we want to change the left pointer equal to mid plus 1, otherwise make r equal to mid minus 1. And if it's able to break this loop, then we just return a minus 1.
2 log n.
So let's run the test case and see if I got this right. And it does get accepted for the test case. Let's submit that. And there we go. So yeah, it's basically 2 binary searches going on, and it's just discovering that pivot. The majority of this code is where you need to find.
You can do that, Park. Yeah, that's one way to do it. That's surely one way to do it. Oh la 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 la. Ooh la la la. Ooh la la la. Jangri boongri jangri boongri jangri boongri jangri boongri. Jangri boongri jangri boongri jangri boongri. It's a funny joke. It's a funny ass joke, man. I'm not doing this shit, bro. It's too difficult. One, I think it's even. Let's look at this. Search and rotate it. Maybe it's easy. Yeah, I don't know how to do this. Lead code 33. Don't really get it. Don't really get it, bro. And this fucking idiot is like, come on, bro. I fuck with all of you guys, but it's like, come on.
Hello and welcome to this video. Today we're going to solve the problem search and rotated sorted array. So in order to understand the solution of this problem, it is necessary to know how to implement binary search and how to find the minimum element in a rotated sorted array. But luckily for you, I have made 2 videos about 2 requirements. So stop this video and go watch them and get back to this one. So let's get started. First, what is the meaning of rotated sorted array? A normal sorted array will have looked like this. But a rotated sorted array is a type of data structure in which the elements of the array are sorted in ascending order. But the array has been rotated by a certain rotated by 3 bits inside the nums array. Otherwise, is return -1. And also you must write an algorithm with O of log n runtime complexity. So the brute force approach to solve this problem is to iterate throughout the rotated sorted array and try to find sorted array. So how do we get the array? Do binary search to find the minimum, which is the inflection point, and return -1. So we return index 4. Then finally we return the max between the return value from the first binary search in the first sorted array and the return value from the second sorted array. So let's jump according to the solution. The first thing we're going to do is to find the minimum point inside. So first thing we're going to do is to find the inflection and implement binary search in the 2 sorted arrays. So let's say we have this input array. We're going to do binary search in 4, 5, 6, and 7 and do another binary search in 0, 1, and 2. It's like 2 sorted array inside 1 array. First, go watch this video where I explain how to find the minimum, which is the inflection point in a rotated sorted array, and go back to continue this video. So once we're going to find the minimum in a rotated sorted array, we're going to implement binary search algorithm from index 0 to the inflection point or to the minimum point -1. So here we can't find the target, so we return -1. And another binary search algorithm implementation from inflection point, or we can name it the minimum, to the last index. So here we're going to find it. It's at index 4, so we return index 4. Then finally we return the max between the return value from the first binary search in the first sorted array and the return value from the second sorted array. So let's jump.
Okay, this is not found here. Okay, and this is found here. What?
Return the max between the return value from the first binary search in the first sorted array and the return. We're going to return the binary search. Also we check well the left. Have found the inflection point. We split the array and use binary search algorithm. Binary search for the well the left is 1. Otherwise,
whoa.
So the time.
Bro, can you like make any more convoluted like bullshit? Like, is it like after neat code? Bro, it's after neat code too. The fuck? The fuck are you doing? Watch some of these videos, bro. Dipshit.
Oh, and welcome to We're Doing
Bro, I don't want to learn from this girl. Jeez, retarded.
To nums of n minus 1, and then back out to nums of 0, nums of 1, all the way back up to nums of k minus 1. For example, 0, 1, 2, 3, 4, 5, 6, 7 might be rotated at pivot index 3 and become 4, 5, 6, 7, 0, 1, 2. Given the array nums after the possible rotation and an integer target, return the index of target if it is in nums, or -1 if it's not in nums. We write an algorithm with O log n runtime complexity. For example 1, our input array is 4, 5, 6, 7, 0, 1, 2, the target of 0, so we output 4, which is the index where our target is. For example 2, our nums array is 4, 5, 6, 7, 0, 1, 2, and our target is 3. Our output is -1 because 3 is not in our nums array. And for example 3, our nums array is 1 and our target is 0, and we output -1 because our target is not in our array. Let's go through an example. For this example, our nums array is 3, 4, 5, 0, 1, 2, and our target is 4. And for this problem, we're going to be using binary search to search for our target in our nums array. And for this problem, we're going to be using binary search, which is a searching algorithm that is using sorted arrays by repeatedly dividing the search interval in half. And the idea of binary search is to use the information that the array is sorted and reduce the time complexity to O of log of n, which was given to us in the problem statement. Our left point is pointing at 3, our midpoint is pointing at 5, and our right point is pointing at 2. And now that we have our 3 points, we want to check to see if our midpoint equals our target. In this case, it is not, because our midpoint is 2 and our target is 4. So now we want to check the left side of our array and see if it's sorted. And we can do that by seeing if the value at our left point is less than or equal to the value at our midpoint, which it is, so 3 is less than 5. So since we know that our left side of our array is sorted, we want to check to see if our left side of our array contains our target value. And we'll do that by seeing if the value at our left point is less than or equal to our target value, and if our target is less than our midpoint. So in this case, divided by 2, and in this case, it'll be equal to 0. So now we'll check to see if the value at our midpoint is equal to, we know it's sorted. So now we'll check to see if our value is in the left side of the array, and we'll do that by seeing if our value at left is less than our target, which is less than our midpoint. In this case, our left is less than our target, but our calculate our mid, and our mid at our index of 1, which is at our midpointer, is equal to. And now we want to loop while our, and now that we have our 3 points, we'll check to see if the value at our midpointer is equal to our target, and if it is, we'll return our mid. It's sorted. In the left side of our, we'll adjust our left is not sorted. We'll check the right side is, we'll. And at this point, we're done with our looping, and if we get to this point without finding our target, we just want to return -1, stating that our target is not in our nums array. That's it for the code, so let's run this. All test case passed, so let's submit. Our solution was accepted, so that's it for this.
It's not the best though, come on. It is a simplistic one, but it's like, it's not even the best. How am I supposed to learn anything from it?
Okay.
Give me the 100%. Yeah, very easy. Yeah, but it's very easy. Bro, what am I looking at? What even is this?
Leak code 33. Search and rotated sorted array. Given a rotated leak code 33. Half of the array is set the left pointer at the first position and the right pointer at the last position of the array. The middle pointer is placed in the middle of the array. First, check if the middle value is 50. No, it's not. Now, check if the right portion is increasing by comparing whether the middle value is less than the right value. Then, check if 50 fits inside it. No, it doesn't. So, we know for sure that our target might be on the left side. Move the right pointer to the position before the middle pointer. Check again if the middle value is 50. No, it's not. Now, check if the right portion is increasing by comparing whether the middle value is less than the right value. Then, check if 50 fits inside it. Yes, it does. We now know for sure that our target might be on the right side. Move the left pointer next to the middle pointer. But why not move the left pointer to the middle position? Since we already checked that the middle value is not our target, there's no need to consider it again. Now, the left and right pointers are at the same.
So why does this not work again? Don't get it, man. Don't get it, man. You're man. Don't get it, man. This shit is fine, man. Bro, don't fucking say that. Some women. One pass binary search. Broken code, nigga. Don't say that. Come on. 2 pass, find pivot and What is one pass and two pass? Test both solution. Don't need to visualize why both fails. Let me see why I'm retarded. Thank you. Thank you, Claude, for reminding me how retarded I am. Thank you. I really love that. Code. Code. Yeah, this is code, bro. Nigga. Could you not open this? Select folder. Hoo. The fuck, bro? I'm not signing in, nigga. Let me just get it. Let me just get. I'm not sign. Oh my god! I'm not signing in. Fuck you. I hate it. I hate what I'm looking at. Okay. Anyways, bro. Shut the hell up, bro. What is two pass and one pass in binary search? Bro, what the?
हेलो स्टूडेंट्स, वेलकम बैक टू माय चैनल लर्न विद पारुल। आज हम एक नया सब्जेक्ट स्टार्ट करने वाले हैं जो कि है डेटा स्ट्रक्चर। पहले जो वीडियोस चल रही हैं वो तो कंटिन्यू रहेंगी। साथ में एक नया सब्जेक्ट भी हमने ऐड कर दिया इसमें, डेटा स्ट्रक्चर। अब इसको हम बेसिक से ही समझना स्टार्ट कर रहे हैं, नेट के अकॉर्डिंग भी हम कर रहे हैं और बेसिक भी हम इसमें डालेंगे ताकि जो नॉर्मल कॉलेजेस के बच्चे हैं वो भी इसे समझ सकें। ठीक है, अब आता है डेटा स्ट्रक्चर मेनली। जैसे कि मैं हर टॉपिक की स्टार्टिंग में आपको बोलती हूँ कि सबसे पहले इंग्लिश का वर्ड आप उसमें से याद किया करो। जैसे डाटा, डाटा क्या होता है? कोई भी रो फैक्ट्स होते हैं, मतलब डाटा को कहीं
Two pass. DSA.
You're trying to get.
What's the difference between two pass and one pass? Let's look at this. Okay, cool. Binary search. Lead code 33.
Okay, let's solve leak code 33, search and
Is it
rotate.
even 100%?
So if we find our result, we're going to return it up here. But if we don't find an easy problem, the code looks pretty easy, but you really have to understand the discrete cases. Like, are we?
Yeah, it's not even 100%. It's not even 100%. Give me 100%. Shut up, fellas. Look here. If it's not good, I'm leaving a hateful comment. I'm leaving a hateful comment if it's not good. I don't want to get my account banned, but bro, what am I doing? Skip duplications. Ooh. Okay. Mid. If okay, target. If is equal to target, I'm just returning true. Oh, it's what the hell. 30, bro, just give me 33. Whoa, 33. We all know what that number means. We all know what that means. Just saying. Just saying. Do I need to know anything before this? I feel like I'm missing a step into fully understanding. Okay. Left half. If nums is equal to, if left nums is equal to, okay, right, okay, else. So we're looking, so explain this code to someone. Who did this? Oh, this guy. Is it even good? Let's be honest here. I mean, yeah, it's good. Okay. So we're doing a binary search on the left. Not really like a binary search. And an if else block going on in here. Asking if nums of left and mid and right and mid. So this will be right and mid, right? Target. What the fuck is target? Oh my god. This leap code question is completely cooked.
Portion being swapped over to the left.
I'm kind of hungry though. Let me get some. Okay, I've decided I'm gonna go on a starvation diet. Okay, anyway. Okay, let's watch something that's interesting for a break. So I'm thinking something like, yeah, how does linear, bro? What the fuck is going on with linear algebra? Genuinely. Yeah, this nigga's like, I don't know. I don't trust Rene Descartes. Oh, that's okay. Okay. Oh. My coordination. Fuck's wrong with me? Okay. Let's look at some math logics.
What is linear algebra? At its heart, it's a way to solve systems of linear equations like these, but its interpretations and applications go far beyond linear algebra.
I'm thinking.
Linear algebra is the study of linear transformations, and it's a way to more easily represent, calculate, and interpret the manipulations of vectors and vector space.
No way. Quantum mechanics? How is that even possible? It is entirely possible the future generation will look back from the vantage point of more sophistication theory and wonder how we can be so gullible. Yeah, I know, bro. Yeah, it's so true. So true, bro. I totally get it. I totally get it, bro.
Hey everyone, today I'm beginning a new series called Maths of Quantum Mechanics. Looking through YouTube, I found a lot of amazing videos giving an overview of quantum mechanics concepts. Things like the wave function, quantum superposition, and even quantum tunneling. But what I didn't find were very many videos giving intuition into the fundamental mathematics behind it all. I was surprised because I truly believe that the mathematics behind quantum mechanics can be made intuitive and understandable. So the point of this series is to take you from someone who knows quantum mechanics to someone who intuitively understands quantum mechanics and all the math behind it. And to give you an idea of what we will dive into in this series, here's a list of the chapters and the topics we will cover.
Why linear algebra? What are nets and wave function? What is in the function? Okay. Quantum mechanics is saturated with linear algebra. It is not just some. Okay.
These are all questions that I remember wanting intuition for when learning quantum mechanics, and hopefully you see questions that you have also always wondered. I plan to add more chapters as time allows, so if you don't see something that you've always wanted answered, please let me know. Now, before we begin, we need to go over the math I'll assume you're already familiar with. First, I'll assume you have a working knowledge of single variable calculus. In other words, you should be comfortable with derivatives, integrals, and Taylor series.
Bro, what are these? Give me some formulas. What the fuck is this, bro? What is this? Oh, fuck. Don't do that. Fuck, I fucked it up.
You don't have to remember how to calculate all these. Just have an understanding of what they are and what they mean. It's inevitable that we'll run into multivariable calculus, but we don't need it for the majority of the series. Second, I'll assume you're familiar with linear algebra at the level of 3 Blue 1 Brown's Essence of Linear Algebra. His series is fantastic, and it largely inspired this one.
letter pissy. It's pissy. And the quantum mechanics, it is almost never denotes the wave function or the state of the system. In an ordinary max, it's a variable name like x or a function. Okay, it's basically x.
We need to
or
go
a
over the
function in
math knowledge,
mathematics.
inequalities, and into more.
And what the fuck is this? Linalge. Now it's the O cut. It's basically a variable dx. In single variable calculus context. It should mean something. And what is this? It's called a Taylor series. Nigga, yeah, I know that guy. Yeah, Taylor, my homie. He was talking that shit, bro. Straight up. Okay, it's an empty set. In the context of integral. Should mean something. Ooh, I can do that. This expression is the inner product overlap of two wave function in a, is it like a physics?
Multivariable calculus, but we don't need it for the majority of the series. Second, I'll assume you're familiar with linear algebra at the level of 3 Blue 1 Brown's Essence of Linear Algebra. His series is fantastic, and it largely inspired this one, so I recommend you go watch it if you haven't already. It will be linked in the description. The linear algebra concepts you should be familiar with are shown on the screen now. Go ahead and pause it to look it over. Again, you don't need to remember how to calculate all these, just have an understanding of what they are. Hopefully this list isn't too daunting, and don't be afraid to brush up whenever you run into something unfamiliar.
Yep, I'm completely familiar with all of that, by the way.
In this first episode, I want to show you all why we want to use linear algebra to model the quantum world. We're going to think like theoretical physicists and find that linear algebra pops out naturally by considering physical observations.
Mm-hmm.
First, let's review the basic mathematical model we have for classical physics. We know that a classical particle carries with it physical quantities, like position, momentum, and energy. As this particle moves in space and interacts with objects, we know that these quantities change continuously in time.
Yeah.
So what are the takeaways? First, we know that classical physical quantities are single-valued, meaning they only
Yeah.
take on one value at any one time. So, for example, a particle can't be in two places at once, and it can't have two different velocities. Second, physical quantities are continuous, meaning they vary smoothly as they evolve in time, and they don't change values suddenly.
Yeah.
Given these two observations, it hopefully seems clear that the way
This
to
is the cope that people give.
model these physical quantities is with a continuous function. A function, by definition, only takes on one value at any single time, and a continuous function doesn't have any sudden jumps. So, this is why in classical physics,
I don't think it's used in the...
we represent physical quantities with continuous functions. Now, this may seem kind of obvious. I mean, what else would we use? Well, to see when a model like this one breaks down, let us analyze a real physical system and compare the classical and quantum worlds. In particular, let's focus on a hydrogen atom, consisting of an electron in motion around a proton. Let's see what we expect to happen within the classical physics framework. As the electron orbits and falls towards the proton, it will release energy in the form of light. This is a well-known fact from electricity and magnetism. By measuring the energy of light released, we can have a measure of how much energy the electron has left, here in units of electron volts. So we can set up a detector and do exactly this. The electron's energy is shown on the left in units of electron volts, and, as required in classical physics, it is single-valued and continuous. Now let's hop into the quantum world and get an actual hydrogen atom and a detector, and let's see what really happens. We would find that we only get a few blips from our detector, measuring only a few energies. Okay, let's reset the experiment and give it another run. We only measure a few energies again, but this time some of them are different. We can repeat this experiment over and over again, and we would notice the following. First, it seems that we only get a certain set of energy values, never measuring anything in between. Second, the specific energy value that we measure is random. However, it does seem like some energy values have a higher probability than others. Let's summarize these conclusions and their implications. First, our experiment showed that physical quantities can sometimes be discrete, meaning we can list all the possible values it can take, never equaling something in between these values. Note that this contradicts the idea that physical quantities must be continuous. Second, the particular value that we measure is random but probabilistic. This means that before making a measurement, we do not know which of the possible energies we will get. However, we do know that some values are more likely than others, so there is a probability attached to each value. Note that this also contradicts the single-valued characteristic, since before the measurement, we cannot determine a singular value for the quantity. It could be any of them. So clearly a continuous function won't work to model the quantum world. So what will? It may seem like a daunting problem to solve, but let's put on our theoretical physicist hats and see what we can deduce from our conclusions. First, let's find a way to mathematically model the randomness problem. It seems like before we make a measurement, the particle somehow holds the information on every possible outcome we could get. How do we mathematically represent this phenomenon? Well, let's say that we know for sure that the particle has energy A, and let us say that the particle is represented by the mathematical object m sub A. Now, m could be anything.
Okay. You have like Rene Descartes. Bro, can I like cancel that?
What is linear algebra? At its heart, it's a way to solve systems of linear equations.
Let's do some matrix. That's my notebook. Fuck. Where is it? It's here.
Everyone.
Is there like a playlist? Yeah, playlist, please. Matrix, bro. I'm gonna break out of the Matrix so hard.
2 pointers. A powerful problem solving pattern.
I'm unironically using it. Yeah, I'm gonna break out of the Matrix so hard. I'm gonna bust in my pants.
Hi guys. So, in this playlist, we'll be solving array problems. Popular array problems that have been asked in popular companies. Okay, so today we'll be solving 2-sum, which is a fairly easy question.
$2D.
Hey everyone.
Pretty sure 2D array is like a thing. Where is 2D array? Matrix should be in Matrix. Bro, 3. Bro, look at the size of this thing, bro. It's crazy. I think I did like one medium search 2D matrix with a binary search. Yeah, it's fucking insane. Ways. Bro, I need ChatGPT. Fuck this. I mean, yeah. No, in DSA. Lead code. Fucking Nick. So yeah, choosing the right method, matrix factorization, complexity. Oh, what? Complexity. For specialized Gaussian elimination. Yeah. Kroiner subspace method. Jacobian Goar. Okay. Linear approximation. DU. Yeah. It's using a upper triangle method, isn't it? I've done this before. Gaussian complexity is pretty cool. Okay, let's go back. Standard traversal. Spiral order. Oh shit, spiral order.
Hey, guys.
We got a look at this spiral out of order. We got a tool song, lead code.
Everyone, welcome back. Now let's write. Everyone, welcome back. Everyone. Hey everyone. Hey everyone, welcome back. Now let's write some more neat code today. So today, let's
I don't even think it's that important, but I want to learn it. It's for the overall understanding. Snake traversal. Like fucking psychology bitches. Okay, common problem solving technique. BFA, okay. Dynamic programming matrix. Cool. Rotating matrix. Cool again. Searching in matrix. Okay. I got it. Working on the weekend like usual. 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 Okay. Oh, don't do that. Don't click anything. I accidentally clicked something. Something might happen. But I'm ready. I'm ready to die. But anyways. This is bullshit. This is bullshit. I don't want to watch this. Let's play some chess.
I've solved 300 LeetCode questions, competed on the national level, got a big tech software engineering job, and even partnered with LeetCode on my social media. But despite all that, I still feel like I wasted my time. Here's everything I did so you can learn from me and do even better. In this video, I'm going to talk about what my motivation was, how I learned everything, what tools I used, was it even worth it, and if I had to relearn everything again from scratch, what I would do. Right away, why did I do it? I'm not going to lie to you. It's not because I found it fun. I would be slamming my desk in frustration, pulling my hair out in frustration, and then it'd be like a slap across the face when the question difficulty would say easy. And I don't care what anybody says. Every single person that started out LeetCoding was exactly like this, struggling with easy questions at first. So if it was so difficult and frustrating, what was the point? Simply put, it's because software engineering interviews are harder than the job itself. Like, you go from solving these incredibly complex, hard LeetCode questions just to get a job where you make a button slightly rounded. Or if you get a complex backend job like I have, you're never even going to use one of these data structures and algorithms ever again. So simply put, I am not ashamed to admit that my sole motivation was the money and prestige that I would get with a big tech software engineering job. If you look at the salary differences from, like, my salary jumped up from $30 an hour to close to $70 an hour total compensation after I got my big tech job at Amazon as a software engineering intern. And the entire interview process was based off of LeetCode questions. So there's maybe 30 minutes where I have to talk about myself. Okay, but how in the world do you actually solve these LeetCode questions? First, I'm going to be real with you. If you are not crazy good with your data structures and algorithms, you have zero chance of landing a big tech software engineering job. So how did I learn everything so you could copy me? I started on the #1 free resource out there, YouTube. Abdul Bari is the undisputed go for data structures and algorithms. He teaches these complex subjects that used to take me months to understand in 1 or 2 YouTube videos, to the point where it gets you questioning, are your expensive ass university classes even worth it when you could just learn everything on YouTube through this guy? And on top of that, a lesser known legend is Michael Samble. He'll recap all of these data structures and algorithms that you need to know in literally 2 minutes. It makes no sense how he does it. This guy. And on top of that, a lesser known legend is Michael Samble.
Michael Samble. Nigga, Michael Sambol. Who would have guessed your name, bro? Who would have guessed your name? Follow you. Textra. Oh, this My nigga, bro. It's like the bro.
Hello, friend.
Nigga. New Matrix. Bro, ain't no way. Look at him. The goat is back.
Hi. The topic is breast.
No way. It's like the fucking Michael Jordan, bro.
Synonyms, circle drawing, algorithm.
Programming concept, cloud computing. Want to learn about binary search. Iterative method. Was I doing the recursive method? Divide and conquer.
Hello, friends. I'm going to start our next topic in algorithms, that is divide and conquer strategy. The first topic was analysis of algorithm. In that topic, I have shown you how to write an algorithm and how to analyze an algorithm and what is the purpose of analysis.
Recursive relation? No way. But why did I know all of this?
Hello, friends.
No, binary search. 2.6. It's wait, I didn't even know there was a iterative method. I thought it was. It's kind of like changing my mind on things.
Now let us write a recursive algorithm.
Bro, this nigga is the back-to-back champ. No way.
Recap all of these data structure algorithms that you need to know in literally 2 minutes. It makes no sense how he does it. I would binge watch these guys' videos and ended up getting me an A in both of my data structure and algorithms classes. While you go through the process of learning these data structures and algorithms, let me put you on to my favorite free tool that I absolutely love sharing. It's a game changer. So this website called visualalgo.net, and they have visualizations for literally every single thing you need to learn. Let's say, for example, you're on the bane of every CS major's existence, linked lists. You could go through and visually learn how everything works, from creating, inserting, searching, and deleting nodes in linked lists, and it shows you all the code associated with those processes right beside going through it line by line. Like, whoever made this tool is just a lifesaver, and I cannot recommend it more. Okay, now that you have the basics down for your data structure and algorithms, we need to get down to the actual solving of LeetCode questions. So what questions did I do? How did I solve them? Why did I pick them? First, let me get one of the easiest mistakes out of the way that I did when I was a beginner. Do not just go to LeetCode and solve every single question you see on there, or picking random questions. This is going to hurt your learning so much, it's going to leave you feeling so frustrated and lost. And that's because there's actually an order you have to follow to learn everything. For example, there's no point in learning how dynamic programming works before you even know how to work with arrays or lists. So what I did is go to this website called Nico. The first thing you'll see is this roadmap, which takes you through everything you need to learn step by step.
Bro, this nigga hasn't even finished.
And you have two options you can follow. They're blind 75 or the Nico 150. Honestly, I would start with the blind 75 to get all your fundamentals down. These 75 questions are the most frequently asked questions in big tech interviews. And in fact, I actually had one of those 75 questions in my Amazon interview. So in order, go through those questions, solving one question every single day. If you get stuck, start by starting that question, go and watch the video solution they have, because it breaks down how to attempt to solve the problem, a brute force approach, and then the algorithm you're supposed to use to optimize your time complexity solution. And let me tell you, get it out of your head that watching these videos is not cheating. Copying these answers over is not cheating yourself out of anything. As long as you understand what's going on and the fundamentals, and you're able to reproduce that a week later, which is why you should be starting the questions, by the way. There's nothing wrong with watching these video solutions. Don't let your ego or pride get in the way in what's already an incredibly complex and difficult thing to do in LeetCode. Now, when you first open up a problem, start by classifying the problem. That includes what data structure it could be or what algorithm is doing. It's okay. Now, when you're done solving this question, you're going to use this hidden strategy. Algo Monster. They're so good because they don't just teach you to memorize, they teach you to math. And it's something called patterns. So once you go through and master those, you don't actually have to memorize all these individual different solutions, which you might be doing right now. And for each of these patterns, there are set templates that you literally just have to learn once and then reuse in every single one of your solutions for coding questions that use that pattern. It's such a good strategy. Now, what I find super cool and unique is their flowchart approach to solving these LeetCode questions. I don't know about you, but especially when I was first starting out with LeetCode questions, I would look at the question and be like, okay, so now what in the world do I do? And this is where the flowchart is so clutch, because it takes you through exactly what you should do based off of what the question is asking you. And then when you actually go and solve the problem, you have an AI assistant to help you. So when you get stuck, don't waste hours and hours frustrated. You just have an AI teaching you. So if you want to join the over 1 million users that got big tech software engineering jobs because of Algo Monster, I highly recommend you check out the link in the description right now. All right, now that brings me to the biggest question. was it worth it? To me, the answer is obviously yes. As I said earlier, I was solely motivated financially. I would not have put myself through the absolute hell that is studying LeetCode questions if I did not get compensated for it somehow, even if it's not directly. And in the end, I ended up breaking into Amazon and Autodesk as a software engineering intern. So in the past 8 months, from just these 2 internships alone, at the age of 21, I've earned close to 50 grand. But that is not the point. What's more important is it kickstarted my career. It helped me finally break into big tech, because something I wish I knew earlier was building out all these coding projects and all for your resume and for your own learning is incredibly valuable and cool. But those only get you the interviews. It gets you to the door. But LeetCode is what pushes you through that door and finally gets you hired. So if you're at a stage where you're getting interviews but you just can't get through them, grind your LeetCode. If you aren't even getting interviews in the first place, work on your resume and build projects. So to end off this video, let me tell you what you should do. Just go through the blind 75 on LeetCode.
We know this. We know this, bro. How much? Bro, I need to flex on these bitch ass niggas, man. 32. Stuff a lot. That's low. That's low. I can't. 3, bro. No way. You kidding me? How much? What's my? Oh shit. 27. 30, bro. I can't be seen with this. This is like blasphemy almost. Anyways, let's see my boy kill all these motherfuckers.
Yeah, our next topic is binary search. Binary search is a searching technique. It's one of the methods for search. There are 2 different methods. One is linear search and the second one is binary search. This binary search follows divide and conquer strategy. If you remember, in divide and conquer strategy, we learned that if the size of a problem is large, break the problem into subproblems. Once the subproblem is solved, subproblems are solved, combine them to get the solution for main problem. So I have already taken some set of elements here. I have a list of elements that is 1 to 15, total 15 elements I have. Now let us learn how binary search works. First and the foremost thing is, to perform binary search, list must be in the sorted order. All the elements must be already in sorted order, then only you can perform binary search. This is a prerequisite for binary search. So here I have the list of elements in the sorted order. Then let us see the approach of binary search. So for performing binary search, we need 2 index pointers. One is low, that is the starting point, and the second one is high, that is at the ending point. Suppose I want to search for a key element, 42, which is already present here. Let us see how binary search works. So I'm searching on mid minus 1, that's 11. For list, see now the list is narrow, 11. Now find out mid, 11 plus 11 by 2, that is 11 only. So mid is also here. Now check at A of mid, do you have that element? Yes, this is the element that I am searching for. So element is found. How many comparisons I have done? 1, 2, 3, 4. In 4 comparison, I got an element which is present at index 11. If I was performing linear search, then I would have started from here and compared each element, and after 11 comparison, I would have got the number. But in binary search, I am able to get it in just 4 comparisons. So that's how binary search looks faster than linear search. So here one example I have taken. Let me take some more examples and quickly solve few more examples. So you do and search works to find out plus 15 by 2, that is 8. So 8 is mid. Is it the element that you're searching? It's 29. Search into. I'm taking a key element. So let us trace this one. This is low, it is 1, and this is high, that is 15. Low and high and mid. So low is 1, high is 15, and mid is 1 plus 15 by 2, that is 8. So we know well that it is low plus high divided by 2 and the floor value. 8. See, one thing if you observe, I have solved already 2 QEs. Every time I was getting mid as 8 only, because for this list from 1 to 15, mid is always 8. Okay, this is interesting. We'll see it further. Now, 8, the key is 30. Is it the key that you're searching for? No, my number is greater than 29. So look on the right hand side. So change low to 9. So low becomes mid plus 1, that is 9, and this remains 15. So 9 plus 15 by 2 is 12. Number is smaller than 9. Now 30 is smaller. So 9, that is 10 minus 1, 9. So both are 9, 9. So this is 9 plus 9 by. Is it the number that you're searching for? No, the number is smaller, so it's on the left hand side. So when it's on the left hand side, we should check this side. So what I should change? High should be changed to mid minus 1. So high becomes 8 and the low is 9, right? High becomes 8 and low is 9. So if you observe now, this 9 side meters like a and an HR low, then less on the left hand 1. So that low is on this side, low and high. Right? Low should not cross high. If low have crossed high means element is not found. So I should run this loop as long as low is.
It is the iterative.
Less than or equal.
Recursively though. So I've been doing iteratively. So this should be.
Let us write a recursive algorithm for binary search. Right? As binary search is following divide and conquer strategy, let us see a recursive algorithm. So here I write algorithm. R binary search. What are the parameters it takes? Low, high, and key. In divide and conquer strategy, we say that if the problem is large, we split it into subproblems and solve. Then you should also define what's a small problem. When do you say small? So if you are able to say this is small, then only you can say the other problems are large. Yes, I say that the size of 15 is large. Then what is small? If there's a single element, then it's small. So how do you solve the single element? If low is equal to high, then it means there is a single element. If low is equal to high, then it's a single element. Then what I do? I check if A of low is equals to key. If it is a key. If it is a key, then return that index L. So if there's a single element that's low and high are equal, then check if that is the key element. This is a single element. See, if it is large, we reduce it to one element. And that one element, if it is a key, then search is successful. Return that index L. If there is a single element and it is not a key, then return index 0. Means the key element is not found. That's it. This is a small problem. If there is a single element, check it is a key, tick it. Otherwise, return 0. If the problem is large, what we'll do? Else. As usual, we know we will calculate mid. Mid is equals to low plus high divided by 2. And we check if key is equal to A of mid. That middle element is a key element. If so, we will return mid. We find out mid and check if that key element is present in the mid. If not, if yes, we will return it. If not, then we check whether it's smaller or greater. If key is less than A of mid, then if it is smaller left hand side, then we perform that binary search recursively on the left hand side. See, for this example, this will be mid, so this is low and this is high. So we perform binary search recursively on left hand side. We'll perform on the left hand side, that is low to mid minus 1. So return R binary search. Low is as it is, this is mid minus 1, and key.
Is this the recursive method?
If key is not equal, key is not less, then definitely key is greater. So look for the key.
Interesting. Interesting perspective. Brute more recursive 2 pass. Is it, bro? Is it the way that I'm doing it?
Key element on the right hand side, that is mid plus 1 to high. Else, return R binary search mid plus 1. We check from mid plus 1 onwards, that is mid plus 1 to high, and key is as it is. Mid plus 1 to high. Mid plus 1 to high and key is.
Yeah, give me a. I think I can do it recursively, right? Recursive solution. Yeah. Alternative, more concise version. Search concise. No, fucking hell. An interview specifically asked, can you do it recursively? They want you to test your ability to translate iterative logic to recursive thinking, your understanding, comfortable with stack frames, okay, demonstrating thinking patterns. So, which is educational, and so is it more? My dick hurts. Is it more no, it is not more optimal for binary search on a rotated array. Let me, in general. I think so. In general, it has to be. In general, recursive is more optimal. No, recursion is less optimal than iterative in most algorithm problems. Recursion is slow. Worse. Recursion is BFS, right? I think so. Yes. Yeah. Bro, it keeps LARPing. I don't like the LARP. Performance overload. Yeah, it is much more performance heavy. Do I even need to learn it? I mean,
is as it is. That's it. Closing of else and closing of algorithm. Now we have written a divide and conquer algorithm, that is recursive algorithm for binary search. Now divide and conquer algorithm, daytime complexities are found using recurrence relation. Let us prepare a recurrence relation for this one. If I say this algorithm takes tn time, then what it is doing, this is a small problem, right? And this is a large problem. So in this one, it is calculating mid and also checking conditions. So if I take the condition, it will check this one or this one, right? At most, it will check two conditions. So I will take these two also. So 1, 1. Then it is calling by dividing the problem into half, either on left side or on the right hand side, any one. So out of these two, it will call itself for t.
Wait. So let's see the solution.
Tn by 2. Tn by 2. And where is the small problem? If list size is 1, Tn are greater than 1, so only 1, and it only Tn by 2. We have already seen it. So the time for this one by applying master theorem is theta of log n. This is 1 and this is 2. So log 1 base 2 is 0 and this is n power 0. So both are 0, 0. So it is 1 into log n and it is 1 into log n.
No, disagree. Agree to disagree. Yeah, agree to disagree on that. Yes, your inherently pivot binary approach can be converted into here's. Is it better? Pure. I don't think it is. Iteration, yeah, obviously. Should I start writing hidden past array itself? Oh yeah, he didn't write a while loop or whatnot. I mean, who cares? Who cares, bro? Recursion relation.
Hi, in this video we'll learn how to trace the recursive function and how to write a recurrence relation and how to solve a recurrence relation. So I'm taking one of the example.
So is trice like a recursive? Is trice recursive? I'm pretty sure it is. Let's go here. trees, of course. Okay. So, okay, bro, this thing it starts at coding. That's what I don't like. Backtracking problems. Okay. Back propagation is different from backtracking. I need to keep reminding myself on that. DFS, it's iterative manual stack. Just using a stack problem with nested structures. Okay. Mathematical recursive definition. In price, it is expensive to do it. Okay. Programming algorithm. Let's do another one. Let's
Hello
do another
friends,
one.
I'm going to start a course on algorithms.
Divide and conquer. What the fuck is this? Priori analysis and posteriori analysis. I'll watch this shit. I need to. How do I watch later? So to play this library. It's everything to do with recursion. Divide and conquer. Okay, it's everything to do with divide and conquer. Greedy method. Okay, dynamic problem method. Graph traversals. For some reason, I find graph traversals a little bit more easier. Just me, I think. NP, hard graph problem. NP hard. The fuck is NP?
The topic is NP hard and NP complete. This is the most important topic and also this is the most confusing topic. But I guarantee that I'll make these concepts very much clear for you. And one more thing, don't watch this video if you are in hurry. Watch it when you are really prepared to watch this one.
Bro, it's like the fucking trice section is itself. The trice structure itself is recursion. Okay. Yeah, I gotta use a lot of recursion methods in trice. Okay. Paste. Don't paste it. What is NP? Let's go. NP hard and complete problems. What is NP? NP stands for non-polynomial time. It's a fundamental concept in commutation complexity theorem. Let me break down. Simple explanation. NP is the set of decision problem. If S is like a decision tree, polynomial time, non-deterministic polynomial time. Is it a decision tree? Question mark. Oh, I hate this fucking. I'm gonna use ChatGPT. Bro, this comment, they hate ChatGPT. No, what is NP? What is NP? What is NP? Question mark. NP can mean different things in context. Nega in DSA. Complexity class in computation, non-deterministic polynomial time. It is also NP if proposed solution can be verified in polynomial time quickly, can be deterministic algorithm. Importantly, NP does not mean the problem is hard. It's only checking the solution is easy. Okay, related NPC. Okay, cool. My nigga's the GOAT. This nigga's the GOAT, bro. It's like a matrix chain. Multi-stage graph dynamic programming. Fucking hell, bro. New matrix chain. Bro. What the fuck? I'm like a level 1 crook. This guy's like a level 99 grand wizard. You know what I mean? Okay, I'm not. I'm about to do the problem, the same problem. I didn't even realize I did a greedy problem. Okay, problem. Oh, this is a lead code, of course. I was like, what the fuck? Submission, course skill system. I don't go fuck, bro. System design. Don't go fuck. Core skills. Implementation of data structure. Resizable array. Okay. Okay. Let's do a binary search again. Valid arranging coins should be useful, but bro, you know what's a crazy thing? If I go here, no, whatever. Okay, whatever. Two-pointer. Two-pointer is pretty similar to that thing. Let's do a two-pointer one. Why not? Threesome. Bro, am I capable of doing this? Let's do threesome. You're given an integer array nums, return all triplets where, okay. I'm going to use, so all the three, so I'm going left to right, and I'm checking left is equal to 0. Let's shoot. And capital N, length of nums, because why not? No, nums. Right is equal to n minus 1. Okay, that is the right, that is the left. While left is bigger than right, this shit is gonna keep going, and I'm gonna find the addition. So left plus right plus something in the middle. What should the complexity be? Should aim space where n is okay. I can do it in enough too, just fine. Okay, that is the goal. And what is going on here? And what's up with this? I need to like do a for loop inside all of this. No, I should have left and right at the same point and keep like moving. Poop, maybe. I don't know. Two-point. Okay, why am I doing all 150? Choose some input array sorted. Maybe. Let's do this. Two integers sum 2. What the fuck is two integer first? Is that a thing? Just don't give a fuck anymore. Okay. Two integers sum 2. Bro. What the hell? I'm a psychopathic killer. No, nothing. Nothing. What the hell? Bro, 2, 8, what the hell? So given an array of integers, numbers that can be sorted in non-decreasing order, you mean normal order, okay? Return the indice of one index of number 1 and 2 such that they add up to the given target, and okay, I just need to like give up the array. They will be always valid solution. The solution must use. It should be like in place. I shouldn't use any additional space since we're assuming index. So, okay. That's not really good for. Can I get another test case? What the fuck? For I in nums, let's do nums. If should I do left, right, or left? Okay, I should do the starting. I feel like, is it these two, or these two, Okay, what should I do? What's the game plan here? Brute force? Nah. Hash map? Nah. Two-pointer is a real homosexual position to have. Okay. Two-pointer is the valid one. I don't know how to do this. Don't know, bro, what the fuck am I supposed to do? Okay, let's do left and right, but it's like, can't I just do like 2 for loops for I in nums, for j in I? I can't. Maybe. Yeah, let's see. That's the whole point of cutting it down. Okay. Ooh. Okay, let's see. I need to find the sum. What if both are starting from 0? And I need to go pick. So if nums of L plus nums of R equal to target, return that's really good. That's fine. I think that's the way to do. So both of them combined, target, return, that thing. But what if it's sorted? So if I couldn't find it, I'm going to move the right pointer first and see if it matches again. That clearly doesn't work. So what if it's 6? How do I do it? So it'll be here. If it's bigger, okay. Okay. So 1, 2, 3, 4. How does it look? I need to return that if it is equal. Else if it is not true, but else if it is smaller, let me cook. I don't think it's the right one. If it is smaller than target, I think the right one, nah. Why did I even put right? What's the point in putting it right? First and second, okay. Let's put first and second. Second. In like every instance, can you do it in like every instance, please? Fucking useless. Second. That's like a better way of looking at it. First and second. No. The fuck. First and second is smaller than target. I should increment the first. If it is bigger, I should decrement it. Bro, I'm such a genius. Okay. I need to go L is equal to no. First plus or equal to 1. Else no. This one. It should be 1, of course. If not, I need to increment both. Is that right? Okay, I need to increment this. Okay, both are here. Okay, let me like put out my drawing skills because that's really needed. Okay, this is first one is here. S is here, first is here. Second is here, first is, fuck, it's terrible. It's terrible. Okay. 1, 2, 3, 4. And the first one is here. Okay, the second is here. The first is here. And I'm checking if these two is equal to 3. If it is equal to 3, let's say it's 6. The number is 6. The target is 6. And if it is not equal, and if it is smaller, which it is, we're going to increment. Okay, fucking hell. We're going to increment this thing. And checking if these two are equal. Okay, it is not. So we're going to increment this and checking if this is bigger than this, right? This is bigger than this, still not. So we're going to increment this now. Now, after that, okay, it's not equal. Now, this needs to get incremented. Now this needs to get yeah, I think I got the logic. Now this needs to get incremented. This is equal. Yes. Okay. So the logic is this and let's do n is equal to length should not equal to n. If it is, we should start incrementing this shit and checking for this. Bro, I'm such a genius. Wow. Return. So if we couldn't find anything, what should I return? Return an empty list. Return empty list. Nums is not defined. What do you mean, bro? Numbers. Bro, stop playing semantics with me, man. It's fucking nums. The fuck you talking is not nums. It's bro. Bro, genius. Oh my god. Fuck. Bro, yeah, fucking hell. Give me that. Expected output 1 and 3. It should have been. I mean, bro, it should have been. Okay, this is the logic mistake. It goes. Okay, I got it. So what happens is. the whole thing stops then. I don't want that. When it reaches the last one, I want this to execute. Why? Because it never stops. Oh, you never find. Bro, this is perfect code. What do you mean? So if first is equal to end of the list, if it becomes the end of the list, I start implementing and checking if this case is true. Okay, maybe not. Okay. So yeah, like what if it's in the middle, right? Can I edit? So yeah, but that's another shit. Okay. Let's put 7. This is the only invalid test case. What the fuck, bro? Fuck no. Okay, let's see what you guys say.
Let's solve leak code 167 to sum 2. So we're given an input array that's already sorted in ascending order, and we want to find two numbers that sum up to some target that we're also given. So in this case, the target is
1. This is not easy. This is medium, actually.
Also given. So
oh, it's 2 sum 2? No way. It's 2 integers. What the fuck you talking about?
Also given. So in this case, the target is 9. The two numbers that sum up to 9 in this array are 2 and 7. And we want to return the indices of these two values, but
I need to get
the
face
catch here...
washed. My shit is itchy.
is that the indexes are 1 based, they're not 0 based. So the first element has index 1, the second element has index.
Bro, 2 sum 2.
Hey guys, Greg here, and let's solve 2sum2, where the input array is sorted. It's a really interesting problem. I like it a lot. So we're given a one-index array of integers numbers. Doesn't really change anything. It's just the way that they're expressing it in the problem that is already sorted in non-decreasing order. Non-decreasing basically just means increasing, but there might be duplicates. So we'll find two numbers such that they add up to a specific target number. Okay, same as 2sum. And so basically, we need to return the indices of the two numbers, index 1 and index 2. And since they're doing one indexed, you add 1 here. You just need to find the two numbers that sum up to the target and return their indices added by 1. The tests are generated such that there's exactly one solution, so you don't need to worry about the case where there's no two numbers that sum to the solution. But this time, we must use only constant extra space. Okay, if you remember how the normal 2sum works, and actually have the same example here, what you would do is you would use a hash map where you make the key be the number and the value be the index, so that you can kind of look up the number that you're looking for. However, you can't do that here because you must use constant space. Okay, you can only just have some pointers, some indices, or whatever. And so how does this work? Well, this only works and it's only possible because the numbers are sorted here. Now, the brute force method that's going to be O of n squared at time is actually going to be a constant space solution. So you can look at all the different pairs. We'd have I starting at here, j over here, and we could move j through. So we'd have a total of 6. That's not right. 11, not right. We could have 12. Nope. 16. Nope. 26. That did not work. You would set I to be over here, and you would start j here, and you'd say, okay, 15. That doesn't work. 16. Nope. 20. Nope. 30. Nope. So then here you'd start to find it. We have I is right here, j is here, and immediately you would find these two. And so that is actually a constant space solution. However, O of n squared runtime is really, really slow, and so you're not going to use that. Now, when the problem says something about it being sorted, and we don't do anything with it being sorted, we're probably not being optimal here. So how do we use this sorted? Well, it's actually by using a two-pointer technique. Okay, so we set L over here, L at the beginning, and R at the end. Okay, so we're calling this a two-pointer technique. If you have it like this, they're usually going to go in towards each other. Now, what are we looking for? We want two numbers that sum to 21. Well, we have a number.
I didn't even realize.
1. We have our other number 25. We could get their sum, and that's 26. Now, this sum is wrong, but it's not just wrong. It is specifically too big. What is the only way to?
So it's sorted, so it's like easier to like know. Okay, I think I know what to do. If nums of L plus nums of R equal to target, return that thing, nums of left, nums of right, that makes sense. If not, else if nums of if it is bigger, if it is, let's say 12, I need to move the right. Okay, if nums, okay, if nums of this thing is bigger, copy, delete all of this shit. If it is bigger than target, I need to move the right pointer one step closer, else if this is this way, I think I could just return an else. Right pointer moves up and it exits the loop. I think we can find a unique solution from this. No, what the fuck? Equal, 2 equal. Fuck's sake. Invalid test case, of course. Oh, what am I doing? Just the index. So, what? Expected output 1 and 3. What are you talking? 1 and 3 what? Oh, okay. Don't do that. Oh, why? 1 and 3. Okay, return L. R? The fuck? What the fuck? What the? That's like the most retarded thing that I've wrote. That's like the most retarded thing that I've wrote. Genuinely. Genuinely the most retarded thing that I wrote. Why am I incrementing this? What's the point? Like I should return. What should I return? Okay, I mean, bro, genuinely, what are these fucking test cases? Blasphemous. So if I run this, why are you expecting 2 plus 4? Okay, my output. Yeah, why are you expecting this? So 1 and 3, so this and this. Brother, bullshit. 1 indexed, okay. It's 1 indexed, whatever that means. Let's look at the...
To make this better, okay? Well, if we move 15 is too small, is going to be big O of n because we're really just moving 1 while L is less than R. You could technically add R. Then if the sum is equal to the target, we can immediately return our answer. We found it, and so we return L and R, except because of this annoying 1 index thing. I don't know why they did that, but you should return L plus 1 and R plus 1. So if we found it, that's great. We will find it eventually smaller. How do we make it smaller? We bring R down by 1. And again, since we're actually guaranteed exactly one solution, we can actually just run and submit this right away. And again, the time complexity of this is going to be big O of n, and the space complexity, as is required in the question, is going to be constant.
1 indexed.
Has index 1, the second element has index 2. I don't know why exactly.
1, 6, 1, 6, 7. Oh, no way. No way I said that. One, 6, 7. Bro, baby sheep. Let's not do that. Let's not show off. Let's not. None of that. Okay, this worked. The next thing. To some input array sorted. Did I do that? I just did that. Threesome. Well, yeah, I don't think I'm not gonna do that. So I'm gonna use. So I have 1, 2, 3, 4, 5, 6, 7, and my 3 sum is 12. So it's going to be 2 plus 4 plus 6, or 6 plus. Well, I have like different. Your output should not contain any duplicate. Return the output in triplet in any order. So any order, the order doesn't actually matter. So yeah, so in this case it's going to be 2 plus 4 plus 6, or 3 plus 2 plus 3 plus 7. So I'm going to use I think, yeah, left, right, and middle index. Oh, that's not even binary search. Fuck. It's two pointer. Cancel. Okay. Boop 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 boop. Booty boop 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 boom ba boom ba boom ba. Okay. So I had like three different options. So I'm gonna use a left index, a right index, and I'm checking the sum with the middle index. So is the sum of these three equal to 12? Kind of. I think I'm just going to switch around the middle index. So is this 12? It actually is 12. So put this shit on the number board. So we have 1. Is this in there? Is it bigger? So it is 13. So 13 is bigger. Bigger means this one should cave in. Is it okay? Another one. So left one comes in this time. Is this bigger? 3 plus. It is bigger. So that means the right one should crumble. It's bigger. Is this yes, another one? Could there be another one? Probably. So this is the framework. So left is equal to, let's code it up. Right is equal to length of nums minus 1, while left is bigger than right. Middle is equal to left plus right minus L divided by 2. And if L, no, if nums, let's take sum. Let's do a sum of is equal to nums of left plus nums of middle plus nums of right. That will be the sum. We need to go if sum of is equal to nums. Sum of is equal to, I'm checking if sum of is equal to target, right? Is equal to 0. Okay. If it is equal to 0, return. Okay. I need to add. I need to get an output thing going on. Output is equal to empty list. I need to append output dot append sum of no, I need to output this shit with commas and shit. I need to append this shit to the output, and that is the sum if it's equal. So sum of if it is if it is bigger. What do you mean is bigger? Okay, this shook if it is bigger than 0. If it's bigger than 0, it's always going to be bigger than 0. Is it? It's not even, bro. Bro, it's not even in ascending order, bro. It's not even in, bro. What the hell? Why is it not in ascending order? What the fuck? Well, if it is not equal to 0, I mean, I need to move the for performative.
Okay, let's solve LeetCode 15 3-sum, the sequel to the popular question 2-sum. So before you solve this question, the first thing you should do is make sure that you've solved 2-sum, which is the most popular question on LeetCode, so you've probably solved it or at least seen it before. I also recommend solving 2-sum 2, which is basically 2-sum except the input array is sorted. A lot of people skip this question. I think that's what makes 3-sum a little harder because they don't solve this one first. If you solve 2-sum and 2-sum 2, this question 3-sum is pretty straightforward in my opinion. But okay, let's get into the question. So we're given an input array of n integers as per usual. This array though can have duplicates as we can see in the example, right? 2 negative 1s in this case. Now what we want to do is find 3 numbers of this array, so A, B, and C, and we want them to sum to 0. So in the example, there were 2 elements, or 2
Hey guys, Greg here. Let's solve 3-sum LeetCode number 15. Now I've actually made a video about 3-sum in the past, but that solution uses a hash map and there's actually a better solution than that. So we're given an integer array of nums and we want to return all the triplets, that is nums at I, nums at j, and nums at k, such that I is not j, I is not k, and j is not k, meaning that they're all three different indices and the sum of those three values add up to 0. Also, the solution set must not contain duplicate triplets. Now they actually do have to specify this case here because if we look at this example, we can see -1, -1, and 2. So that works because these two are actually different -1s. They're different indices. They're different locations in the array. These j and k, which are generic variable names, we're going to then from low we have another -3, and from high we have a +3. This is is going to equal -3, and that sum is too small. We're looking for a sum of 0. So we need to try and make our sum bigger. To make our sum bigger, well, it's sorted. So we can actually guarantee that if we move high to the left, that's the wrong thing to do, because that would make our sum smaller. If we move low to the right, that's guaranteed to make our sum a little bit bigger. Actually, it's not, because if you had another -3 in this position, well, then this wouldn't actually change it at all, and so that wouldn't be very helpful. But luckily, this is a -2, so this will make our sum -3, and then -2, and +3.
Okay, that should work. Bro, what the fuck is he looking at? Okay, let's any YouTube messages? Anyone? Let's see. It is going to be a 12 stream, so I'm expecting a lot of questions. A lot of questions. Let's see. Whoa. What the fuck? It's going to be a 12 stream, so that is weird. Hurt in my right eye. I don't know what it is. But yeah, let's go. Let's go with the lead code. This is threesome. The next one is going to be even better.
Okay, let's solve LeetCode 15 threesome, the sequel to the popular question twosome. So before you solve this question, the first thing you should do is make sure that you've solved twosome, which is the most popular question on LeetCode, so you've probably solved it or at least seen it before. I also recommend solving twosome 2, which is basically twosome except the input array is sorted. A lot of people skip this question. I think that's what makes threesome a little harder because they don't solve this one first. If you solve twosome and twosome 2, this question threesome is pretty straightforward in my opinion. But okay, let's get into the question. So we're given an input array of n integers as per usual. This array though can have duplicates as we can see in the example, right? 2 negative 1s in this case. Now what we want to do is find 3 numbers of this array, so A, B, and C, and we want them to sum to 0. So in the example, there were duplicates, but the B was negative as obviously 0. So to our solution set, we can say, okay, there's a negative 3, a 1, and a 2. So now when we move, we can consider this as our first element, right? But eventually we'll see that we go through the entire thing and we don't find anything that can be added to 3 that'll give us a sum of 0. We'll do the same for this one, and there isn't anything. Now we get to a negative 3 again though, because remember there are duplicates in this array. So now we're saying again that we're going to put negative 3 in this first spot. Now this is a recipe for finding duplicates. This is not good. And we'll see in this example that's exactly what's going to happen. There's another, we'll take this as our B, we'll take this as our C. Again we find negative 3 plus 1 plus 2 sums to 0. So then we're going to add that again to our result set, right? But that's not what we want. We want to eliminate the duplicates. So the problem was we took negative 3 as our A value, right? And then we searched the rest of the array for 2 numbers, 1 and 2, that add to 0. But then we went back here, right? And we found the negative 3 again, and we did the exact same thing. The problem is we don't want to have the same number in this position, in the A position, twice, because then if there are the numbers that come after it, we could potentially find duplicates. The solution to this problem is to sort the input array. Let me show you what I mean. So here you can see that the array is now sorted. Let's cross out our top array, which was unsorted. So now we are going to sort the input array. So now when we're looking for all combinations, if we find negative 3 first,
then that's good. Okay, we'll say negative 3, then we find these two numbers, 1 plus 2, and then we find our solution. Great. Now if we get to negative 3 again, we'll say, hey, wait a minute. This number was already in this position, right? And we know that because its neighbor, its left neighbor, is the same value. We don't want to put it twice here, because if we do, we'll get the same duplicate. So we're going to tell ourselves that we already computed all combinations that start with a negative 3. So we don't need to do that anymore. We already visited this one. We're going to skip this one, and then we're going to go here. So that means in this case, we're not going to find any more results in the remaining portion of the array because they're all positive. They're never going to sum to 0. So then in our result, we're only going to have the one triplet 2 sum, and you probably are shifting x. And even we are not doing the brute end. So for the implementation I'm showing, it could be big O of 1 or it could be big O of n, because sorting actually does take extra memory in some libraries. So it depends on your implementation of sorting. It could be O of n, possible first value. The remaining portion of the array to basically solve. If only I could type today. If it's too small, we need to make it bigger, so shift our left pointer to the right. The way that you can do it with writing to get it over here, right? Now in num is equal to left is equal to nums of left minus 1 by itself. We don't even have to worry about it. So in this case, we're only going to shift our left pointer. Because we don't want to have the same sum, we're going to have to use a loop. So in this case, if nums of left is equal to nums of left minus 1, that means it's the same value, so we have to keep shifting our pointer. But remember, we don't want our left pointer to ever pass the right pointer, so we're going to add that to the condition. So this is all we needed to do. Now I believe, unless I've made another stupid bug, we should be able to just return our result and pass the problem with the most optimized solution. Okay, I'm praying that this works on the first try. Let's see. We passed the test case, the first test case. They really want you to buy LeetCode Premium. This is taking... Okay, so it did pass. Usually I have some stupid bugs where I mess up a condition, but okay, so we
we passed it. This is pretty complicated. I'm not going to lie. This is a pretty hard problem to solve if you've only just solved 2-sum. So I really recommend solving 2-sum 2 as well before solving this problem. I might have made it look easy with the amount of code I wrote, but don't let it fool you. I really struggled with this problem the first time I was doing it. Hey. Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem rotate array. We are given an array and we want to rotate the array space. Right, k is 2 in this case, so we're going to this just 3 it into in the same opinion. So let's get into the code and we're copy and pasting. You could put this elements. Let's do the remaining portion from K until the end of the array. And, that's all we really are updating. So you can kind of guess how this helper function is going to be structured, just passing in two different values for left. Hope that this was helpful. If it was, our code, as you can see,
Okay. So I've been speaking to myself, but it is what it is. So yeah. So what I'm doing is I'm multiplying this by this. So I'm multiplying whichever the smallest min of L comma R divided by length of nums of minus. Bro, I'm such a genius. Wow. How did I figure that out? So what will be, so if output is equal to 0, so what is going on? If 7 comma 6, okay, if minimum of multiplied by length of L minus, which is the bigger, okay, R minus L, bigger than output, I need to change the output, and I also need to increase the left pointer. Is that right? So I need to increase the left pointer. How do I know I should increase the left pointer or the right pointer? How will I know which pointer to increase? If this is always going to be bigger than the output, so I need to change the output. So left increase 1. This is actually an interesting question. So let's say this, fuck, I can't draw the fuck. So this right here is like really big here. So how do I know it's like really big? This is the biggest thing, biggest cock. So the water level becomes here, right? How do I know I need to choose this instead of, let's say this is over here. This is really tiny. So at the beginning, it's going to be like, the water is going to be like here. And we're going to store that. At the second one, the water is going to be here. And we're going to store that. And the third one is going to be, we're going to move this one here to try. Okay, this is bigger than this. And we need to check. Okay, I think I know what to do. We need to check if L plus 1, if num plus 1 if it is bigger, if the second one is bigger, I think we need to move the pointer, give the preference to this one. If it is not bigger, if it is small, we're going to give a and, bro, I'm gonna cook. I'm cooking. Fuck. I'm cooking so hard right now. It's crazy. And right should be bigger than the nums of right minus 1. Right minus 1. Right plus 1. Right. If both of them are met, the left pointer will be moved. If one of them doesn't get met, the priority will switch and not. So the priority still remains with the left pointer right now. So the left is equal to, this will happen. And what else? Shik. And I need to, after all of this, I need to update output is equal to this thing right there. Bro, if it works, I'm gonna cry. Of course it didn't work. Bro, just have it called nums, bro. The fuck you mean heights? Okay. Fine. I don't need length. I just need a R minus L2 index. Same thing. What's happening? Bro, this is so fucking smart. I need this to work. It's crazy. So what is happening here? If this is bigger, okay, let's Okay. If let's print something. Is debugger prod. Print fucking hell. Any recs printed? No. Any rec? No. So what is, I don't need this. Maybe I need this. If rec is bigger than the output, in this case it's not. Okay, it's gonna stop. I don't want it to stop. Okay, all is gonna be like bigger, of course. It's gonna be bigger. Bro, it's such a genius idea. I think I got this. I think I got this. So just fix. Ah, okay. Reject all. And course, this is what I meant. This is what I meant, of course. Yeah. If nums of L equal to nums of elegant code. That's what we like to see. I can't, bro. Good intuition, but oh my god, I should have. Oh, fuck! I should have got it. I think I can do it. So if nums of L, why L? Because obviously if it gets closer, it doesn't make sense. Okay. So I mean, don't you have to like be worried about? Okay, you just have to be like, still though. Okay, you're just pushing the left side, but what if? Here's the thing. What if this one is really fucking big? Maybe it doesn't matter. So this one is really big, so you can like do that. But what if this is like really tiny? And you're just like stuck with it. You're just doing this all the time. Right? If nums of L, yeah. What are you going to do then? What if the last element is like really tiny? Test case. What if the last element is like 1? Right? Why is it invalid? Why is it invalid? Like I think that's the test case that I was thinking. But why is it invalid? Why can't the last one be really small? Somewhere in the middle, it peaks. Why does the last one have to? Yeah, it is what it is. So I got this intuition down, kinda. The output, I should have got it. This intuition down, but obviously, yeah, normal output, and I need to. Output needs to be this thing. I'll do area. Area is a little bit more elegant. So what is this?
Hey everyone, welcome back, and
11.
let's write some more neat code. So today we're going to be solving LeetCode 11, container with most water. So we're given Hey everyone, welcome back, And let's write some more neat code. So today we're going to be solving LeetCode 11 container with most water. So we're given an array of heights. So this is a height 1, this is a height 8, 6, so on and so on. And using these heights, we want to see what's the biggest area we can form with a container that has a left height and a right height. So in this example, you can see that if we take this one with a height of 8 and this one with a height of 7, we can create an area. Let's see how wide this is, like 1, 2, 3, 1, 2, 3, 7 wide and 7 tall. So that's 7 by 7, and the area is going to be 49. And they tell us that much in the explanation. So since we're given a list of heights and we want to maximize the area, we can potentially just take every single combination, right? So check every left pointer and every right pointer. So my first thought with this is, what's the brute force way? What's the easiest way to solve this problem? Well, let's just try every single combination of left and right. Let's just try every single possible container we can make and see if it works. So let's say this is our left and this is our right. What's the max area we can make with this? Well, let's fill it up to 1. And if we keep filling it up with water, notice how it's going to spill to the left, right? So this left pointer is our bottleneck, right? We have a height of 1 and we have a height of 7. The minimum one is 1, so we can't fill it up any higher. The width of this is also 1, so we get this one, that's going to be 5, and we can just keep going. The height is going to stay 1 because our left pointer has a height of 1. Next, we move our left pointer here. And again, we're just going to continue with the brute force solution. Eventually, we're going to have our right pointer set single position at least once. This is the brute force O of n position ahead by the height of height. Now that will actually work in LeetCode. Let's see if we can try. So the first update our point for us, we've of 3. Side is at 4. We could choose to shift this one just because we know that a larger height exists over here, but it actually does left pointer. Now we get a 2 by 3 rectangle, which is too small. Let's shift our left pointer one more time. Hey, this time we got a 5 by 2. That's a little better than before, but still not better than our max. And so this is basically the last rectangular water container that we can form. It's going to be 4 by 1. And now if we try to shift our left pointer, we get to the terminating condition. We get to the condition that's going to end our code. So now that we shift our left pointer here, we're going to get our left here, left and right are at the same position. So let's get rid of this. Let's get a solution that can actually work on LeetCode. And maybe you might need this solution in your interview if the brute force is not good enough. So once again, I'm going to set our result equal to 0. I'm going to do what I did in the explanation. Our left pointer is going to be initialized all the way. And I'm just going to copy and paste it from my above solution because that's what the brute force solution is for, right? You can learn the basic parts of the problem before doing less. Is if they're equal, right? That's our else condition. And remember how I said we could do either one if they're both. One more time, and this time will work. So this is the actual linear time solution, the big O of n solution.
Why does this shit is always really bad? 11, right? It's to 11. So we have and right being the length of nums. And the output, fuck you. Why did I do that? I don't know. So while L is bigger than R, and what are we doing? Are we comparing? So formula for this is, bro, it took me like a while to like formulate the formula too. So that was like really smart of me. So the area is equal to minimum of num L, comma num R multiplied by, that stuff is multiplied by the actual indices. No, R minus. R is the bigger one, that needs to be minus. So yeah, that is the gist of it. So I need to check if output is going to be, obviously output is equal to max of area on output, because sometimes the first iteration might be the biggest one. So first area and output, and we're gonna go to code, and if, so what I'm trying to do is I'm trying to check if nums of L, if it is bigger or equal to nums of are, we're going to stop the loop, and it's going to be if nums, we're going to increment the left, we're going to prioritize the left dice first. It's going to go here, and else it's going to be a easy little else block, formalizing this thing, and boom, and yeah, you just need to output. Yeah, sorry. This is not what I came up with, but 92, that's cool. Memory is not the best. Let's look at what the fuck is this code, bro? Yeah. Sure, bro. Sure, whatever. Interesting. Okay. What is the 100%? Is it 100% just my code minus maybe like minus this? I don't know. Doesn't make sense. They could just like put it L maybe. It doesn't matter. It's kind of irrelevant at this point. It's two-pointer approach. Max area. How is this? How is this any better than mine? Oh, it's like one-liner code. Wow, bro. Wow. How did you even like compute the area? I just like wrote it in one little code. Okay, fine. Fine. I think this works. Bro, I literally like did nothing. What the fuck? Whatever. Let's go. Linked list, not my favorite thing. Trees, kind of my favorite thing to do, but I need to work my way up a little. Sliding window, who cares? Bro, linked list isn't even like, maybe is linked list recursive? Pretty sure. Doubly linked. Abdul.
Hi, welcome to my course. I'll guide you how to follow this course.
What the fuck? Bro, this nigga's cracked. What the fuck? Essential C++ and C and C++ concepts before we start. Sparse matrix, matrices. Oh my god, strings. Okay, binary tree, fucking goaded, heaps, sorting, graphs. Okay, linked list.
Now this section is about linked lists. So in this
7 hours on linked list. Holy shit.
Video, we will learn why we need linked list. So for covering the topic, I'll be discussing about these two things, problems with arrays and the difference between array and linked list. So first thing, problem with an array. Array is of a
Can you like timestamp it, please? Okay. Is it a good idea? Probably, right? Okay, that's the plan. Okay. Unfortunately, is linked list. I don't think linked list is that useful in trees. If I'm being completely honest, I don't see the. It's a lot of recursion in linked list. Trees are closely connected. Trees extension of the linked list idea. Okay. How the fuck? AVL trees, search trees, heaps, sorting techniques, graphs, asymptotic notation. Holy shit, bro. This guy's the fucking goat. Holy. Bro. Bro, why is he moving like... He's moving crazy. So what is the linked list? 6? No. Linked 11. I think that's
Hi, welcome to my course. I'll guide you how to follow this course. This course is covering around 45 hours. Then it means you have to spend some extra time for learning this course. So I suggest you to complete this course in a timely manner. So you spend at least 2 hours per day so that you can finish it within a month. Then while studying, you can watch whiteboard session, and whatever is discussed in whiteboard session, you can prepare notes if you want. And every program is
Bro, this is fucking gold. Let's go.
Our next topic is sparse matrix. A matrix in which there are more number of zero elements are there. I have an example matrix of order 8 by 9. And in this section, we'll be learning about special matrices. Special matrices are square matrix. That is, their dimension is n cross n or n by n. For example, if it is 5, then it is 5 cross 5.
Bro, this is gem. Gem alert. Did I just like fumble into the gem? What? No fucking way, bro. Bro.
5 rows and 5 columns. So matrices are square matrix. This is the first thing. And the second thing is they are
Nigga, this is like crazy.
having more number of the functions that we have discussed, that is set and get function. So first function I will write on set. Set topic is binary.
2 point, I see like probably doesn't do 2 point here. Hashing techniques, sorting techniques, okay, keep, search trees, queues, strings, array representation, array ATD.
Now the topic is array ADT, that is array as abstract data type. Abstract data type means representation of data and the set of operations on the data. Now, array is a basic data structure provided by almost every programming language, like C++ provides an array as a basic data structure. So representation of data is defined by the compiler itself. Now the operations on the data is not given by the compiler. We are supposed to implement the operations or provide the operations on array data structure. So data structure array and the set of operations together, we can call it as ADT. So basically we will be learning how we can perform various operations on an array. So here is the list of operations that are possible on an array, and many more operations are possible. So some of the operations here we will discuss in this video, and more operations I'll show you in the coming lectures. Now I will quickly read out just the set of operations here: displaying an array, adding or appending an element in an array, or inserting an element at a given index in an array, deleting an element from a given.
It's not even sorting though. It's binary search. Binary search trees.
Topic is binary search trees. So in this video, we'll learn about what is binary search tree and the properties of binary search tree. So here is a binary search tree. Let me define it. It's a binary tree in which for every node, all the elements in its left subtree are smaller than that node, and all the elements in the right subtree are greater than that node. So if you look at this also, elements in the left subtree, there is only one element that is smaller, and here the element is greater. For this node, this is smaller. Hi, in this section, I will be revising the concepts of C and C++ programming, and I can use it 2 times. So this is 6 and 7. That's it.
Fucking this nigga, bro.
In this section, we will learn about strings. So first of all, in this video, I'll give you.
Okay, I need to. That's like a way I need to like approach this. I think linked list is the way that I'm gonna do it. Also, I need to like learn C++, then C, then Holy C. That's the way to do it, I think. Bro, I'm getting. Ooh, let's go. Look at this, bro. Look at this. That's what I'm talking. That's what I'm talking, bro. Linked list. Nah. Search and rotated arrays. What the hell? Yeah, this one. It's conflicting interest. Just say it like that. Threesome. I don't think I can. So I need to learn all eyes on me. Ooh, look at that. That kind of motivates you a little, I think. But why am I just 13 questions in line 73? What the hell? It's not really that important, I guess, but fuck, I need to max it out. Damn it. I need to get a holistic understanding of programming language in general. But the top tree is looking voluptuous, I should say. Look at the top tree. Bro, it's looking good, bro. It's looking good. That's all I'm gonna say. It's looking good. So, Barry doesn't have. It's looking good though. It's looking good. So this is the main thing. 90% of the shit comes from here. So. Should I go stack? Stack is like the most useless thing, but I think it comes with a lot of recursion problems. So I think it's decent enough to like for me to know it. But linked list, obviously. Linked list is recursion using a dummy node and all of this bullshit. So I'm trying to think, should I do linked list? Greedy? Definitely not. Definitely not greedy. But That's my boy. He's my boy now. You know what I'm saying? Boy. Let's do
The
matrix.
variable of type matrix. In this section,
Let's do matrix. That's what I need to do. Matrix, it kind of like goes really well with, I don't know. I don't know. Problems. I'm going to do matrix. Hopefully it has some, let's see, matrix. It has, no, I need a topic. No, brother. Tags, take it out. Hash map, hash table, matrix. There's a lot of overlap with dynamic problems, binary search. I mean, this one is binary search. Backtracking, binary search, dungeon. Okay. Let's only do easy and medium. Difficulty, easy. Easy. Matrix, DFS, 2-point, geometry, simulation, sorting, binary search. Okay. That is something we said. Okay, let's do binary search to get our panties wet. Count the negative numbers in sorted matrix. I think I can do this. So on this matrix, I count the negative one. So for I in fuck, I need a is it cold? Kinda. So there are 8 negative numbers. So am I counting? Okay, I'm counting the negative numbers. Why am I using binary search again? So I'm just gonna go over. Could you find? I don't know. I need to go over. How do you do that? How do you even like do that? There's no shame in it. This is my first on this topic, so I can be liberal with how I do it. Lead code.
Hello everyone and welcome back. Today we're tackling LeetCode problem 1351, count negative numbers in a sorted matrix. This is an easy rated problem, but it has a very cool optimal solution that is a classic interview pattern for grid problems. We're going to break it down step by step, starting from the basics and moving to the most efficient way to solve it. First, let's understand what we're being asked to do. We are given a grid, which is just a matrix of size m by n. Our job is very straightforward. We simply need to count how many negative numbers exist inside this grid. But there's a catch, or rather a helpful hint. The grid is sorted. Specifically, it is sorted in non-increasing order, both row-wise and column-wise. This means if you look at any row, the numbers go from big to small as you move right, and if you look at any column, the numbers go from big to small as you move down. Let's clarify exactly what we're working with. Our input is this grid of integers. The most important property is that sorting. Because rows and columns are sorted in descending order, we know that all the large positive numbers will be bunching up in the top left corner, and the negative numbers we are looking for will be concentrated in the bottom right. In the example shown here, we have a 4x4 grid. If you manually count the negatives, you'll find there are exactly 8 of them. Let's walk through that example manually to see the pattern. In the first row, we have 4, 3, 2, and then -1. That's one negative number at the end. In the second row, same thing, just one negative at the end. In the third row, we have +1, and then it switches to -1 and -2. That's 2 negatives. And finally, the last row is entirely negative numbers. If we add those up, 1 plus 1 plus 2 plus 4, we get 8. Notice how once we hit a negative number in a row, everything after it is also negative. That's going to be key. Just a quick heads up before we jump into the logic. We'll be walking through the solution using Python. But don't worry if that's not your main language. I'll be showing. We get 8.
It's randomly sorted. It's not randomly sorted, okay. So interesting.
Notice how once we hit a negative number in a row, everything after it is also negative. That's going to be key. Just a quick heads up before we jump into the logic. We'll be walking through the solution using Python. But don't worry if that's not your main language. I'll be showing the full code for Java, C++, and JavaScript towards the end of the video, so stick around for that. So the first logical approach, especially if the matrix is very wide, is to use binary search. We know each row is sorted in descending order. Instead of checking every single number one by one, which would be...
So each row is sorted in the binary order. That means I would know the first... How do I know?
Be the brute force way. We can binary search each row independently. For each row we want to find the index of the very first negative number. Once we find that transition point, we instantly know that every number to the right of it is also negative, because the row is sorted downwards. We just do this for every row and sum up the counts. Before we look at the code, let's talk about the real reason people fail at LeetCode. It's not because they can't reverse a link.
Okay, let's try this. So def I don't like using self. Left, comma, right. So it's gonna be while, okay. Is bigger than grid of R. I'm gonna. I don't think I should return anything. I should. Okay. What I'm gonna do. If that left, if the right is bigger than the middle, if the right side is bigger, is equal to Gree. You know what I'm saying? Bree is bigger than target and she. How do I mention it? It's, I don't think I need to do this. Okay, if degree of middle is equal to target, then what should I do? Return degree of left. This would have been fasten if I know the binary search by heart, but I don't. That's fine. Degree of right is bigger. If the right one is bigger, as it should be, we're gonna increment the left. Else, okay, I don't even need a binary search. What am I doing? I don't even need a binary search. Holy shit. Hopefully that has no mistakes. What's the mistake in that? Should I have this? Should I have Bro, stop hurting my feelings. That's really not nice. Fucking. No, bro, don't give me the fucking code, please. Yeah, well, this is the code. How does it work? For row in grid, okay. Brother. Bro, yeah, implement a simple binary search. Oh my god. So blindingly obvious, but I'm trying to do something fancy. Yeah, 0. Okay, no. While. Should I even do that? Yeah, count. Just count. Count is equal to 0. While. No. For loop. Okay. For row in grid, L is equal to 0, R is equal to len of nums minus 1. And I need to check if the row of left is bigger than the row of right. If it is bigger or equal. Okay, while, fuck. I need to implement, so if okay, I need to check if row of mid bigger than row of right. If so, so this one mid would be 3. What do I do if count all of them? That can be bigger. So if that's not the case, bro, you guys are like doing too much.
Linked list. It's because they break their daily streak. I built my daily to-do specifically to solve this. You can set solve daily leak code, but every time I ship and a right pointer at the end. We check the middle element. If the middle element is negative, it might be the first one, or there might be more to the left, so we move our right pointer to look at the left half. If the middle element...
Okay, I need to check if it's 0. Okay, cool. Got it. Check if it is bigger than 0. Right, if it's bigger than 0, then count, yeah. So half of this is coming to fruition, so row of mid. This is so mid. So let's just look at this. Right is equal to, okay, we are moving the right pointer, fine. So right is equal to right mid minus 1, minus or plus minus 1. Okay, else, I mean there should be an else if, no, that's brutal. That's brutal mog right there. Else L is equal to so I need to count is equal to plus or equal to length of grids. Oh shit. Minus left. The entire grid. Bro, how do you even come up with that? That's like the most bullshit, stupid shit that I've seen. Okay, let's. Nigga, show it in Python, man. Fucking chess. Okay, this is clearly not staircase traversal. Okay. Matrix DSA. Clearly something is not right there. Fuck you. Niggas do all of this shit just to get slimed out. Isn't that crazy? Count negative numbers. Count.
Will be learning about special matrices. Special matrices are square matrix, that is their dimension is n cross n or n by n. For example, if it is 5, then it is 5 cross 5. 5 rows and 5 columns. So matrices are square matrix. This is the first thing. And the second thing is they are having more number of zero elements.
Written count. Bro. Levi Sandalus. Crazy. Who was gonna Sandalus? Supermarket. Okay, I don't get this. Ooh, is it used in AI/ML? Heavily, right? Heavily.
If there are more number of zero elements, then
let's see what we
So before we start, so I just wanted to give you the crux of solving, let's say in an interview you're given any matrix problem, right? So the thing is, whenever any matrix problem is given to you, so how you're going to approach, how you're going to think in that direction, right? Because the thing is, you hardly have around 5 to 8 minutes of time to think. The interview will give you around that much time, correct? So the thing is, you need to think.
Bro. Just give me an overview on matrix, please. I like this matrices DSI. Yeah. Fuck. Let's go. Let's go, bro. Placement.
What are the chances of you knowing what this is? Yes, you got it right. This is a table, something that you use to organize data using constructs like columns and rows. However, did you know that a table is also known as a matrix? A matrix is a type of a multi-dimensional array, and is one of the most popular data structures covered in coding interviews. In this video, I will discuss the most important aspects about matrices and how to implement them. Hi, my name is Ricardo Ferreira, and I'm a developer advocate here with AWS. Welcome back to this series about data structures. In this episode, I will talk about matrices. The matrix data structure is widely used in many fields, such as linear algebra, computer graphics, and statistics. But I am almost sure that this is not the reason why you are here today. Chances are that you are here because, number one, you are a software engineer. And number two, matrices are heavily explored during coding interviews. Why matrices are so popular? Well, because they enable the efficient storage and manipulation of arrays. During coding interviews, developers are frequently required to solve problems involving two-dimensional arrays. And the problems vary from things like printing the matrix values in the form of a spiral to something even more elaborate, like in place rotating the matrix by 90 degrees in clockwise direction. In addition, you may see sorting algorithms like quicksort being used along with matrix implementations. Overall, the matrix data structure is a versatile tool that frequently appears in coding interviews, therefore being an invaluable topic for you to learn while preparing for one. In this case, let's get to work. A matrix is a two-dimensional data structure that is used to store and manipulate arrays in a tabular form. It is made up of rows and columns where each element of the array is referred to as a cell. Imagine, for example, a spreadsheet where each row represents a record and each column represents a field or an attribute of that record. In a matrix, you can access individual elements by their row and column indices. In the spreadsheet example that I just gave you, let's say you want to retrieve the column first.
Yeah.
First name.
Retarded.
You could access the first name value for the first row by using the notation matrix 0 of 1, where matrix is the name of the matrix and 0 and 1 are the column and row indices, respectively. Matrix data structures are commonly used in mathematics, physics, and computer science for solving linear equations, representing graphs, and performing matrix operations such as addition, subtraction, multiplication, and transposition of data. They are also used in programming languages like MATLAB, Python, and Java for scientific computing and data analysis. Overall, matrices provide a convenient way to organize and manipulate data in a tabular format, making it easier to perform calculations, analyzing data, and represent complex relationships between variables. Matrices have several advantages. For example, a matrix data structure is a collection of rows and columns that are arranged in a grid-like fashion. The structure of the matrix allows for efficient storage and retrieval of data. It can also be used to represent and solve a wide range of mathematical problems, such as linear equations, vector spaces, and agent values. It is a powerful tool for data analysis and visualization of data, as it allows for easy manipulation of data and the ability to see patterns and relationships between variables. However, just like any data structures, matrices have disadvantages. One of the main disadvantages of
Let's discuss matrix chain multiplication. But first, let's understand how many operations are required to multiply two.
Let us talk about multi-dimensional arrays in C++. Here is a simple program. I've created an array of size 3 cross 2. It's a 2D array. There are 3 rows and 2 columns. And the values in the first row are 10, 20, values in the second row are 30, 40, and values in the third row are 50, 60. So we have 3 rows.
Multi-dimensional arrays.
In this presentation, we will learn the concept of address arithmetic in case of multi-dimensional arrays. So let's get started.
Is multi-dimensional array and matrix the same thing? And matrix the same thing. Let's cancel. That's 29. So but they are closely related. It's a mathematical concept more than anything, most of the time. 2D, okay. Bro, you wanna see a high IQ move? I'm so fucking smart. This is exactly why I think I'm one of the smartest human alive. But you may disagree. I don't care. I don't care that you disagree. Let's fuck you. Multi-dimensional. No. So I want to learn about multi-dimensional arrays or matrix. So matrix DSA. I want to learn about matrix, bit magic. Okay, I'm gonna.
We hope we pray for better days.
Nigga, where the fuck is data matrix? DSA. Yeah, of course. Let's look at it.
同学们，大家好。那从今天开始，
Nigga, I just wanna learn matrix, and he's gonna go into heavily. It's not like deep enough, you know. But deeper. Okay, let's.
Introduction to strings.
Let's go to matrix, brother.
A variable of type matrix M. And let us set the dimension of this one as a. In this section, we'll be learning about special matrices. Special matrices are square matrix. That is, their dimension is n cross n or n by n. For example, if it is 5, then it is 5 cross 5. 5 rows and 5 columns. So matrices are square matrix. This is the first thing. And the second thing is they are having more number of 0 elements. If there are more number of 0 elements, then we can handle them specially and store only non-zero elements and avoid storage of 0 elements, so that space can be saved as well as computation time can be saved. So we'll be learning about all these matrices one by one. I'll just read out their names. That is diagonal matrix, lower triangular, upper triangular, symmetric matrix, tridiagonal, band matrix, triplets, and at last we'll learn about sparse matrix. So let us start with diagonal matrix. This is a diagonal matrix. I have taken a diagonal matrix of order 5 by 5, that is 5 rows and 5 columns. And here you can see that most of the numbers are zeros, and only the elements in a diagonal are non-zeros. So the important thing is, other than diagonal, all elements must be 0, then only we say it's a diagonal matrix. Suppose I have some element here, let us say 5, then it's not a diagonal matrix. This must be 0. So the important condition is all those elements must be 0. So let us see how we can define this one. See, if this is a matrix M, then M of ij is 0. If I is not equal to j, M of ij should be 0. If I is not equal to j, then it is a diagonal matrix. If they are equal, then the elements may be 0, non-zero. We don't bother about that. We bother about rest of the elements. All these elements must be 0, and these elements are 0. So these elements are not
History.
So before we start, so I just wanted to give you the crux of
Can I do the problem? Like, can I do the problem or something? It's like, I feel like if I can do it, I would have a better understanding or something. You know what I mean? So, don't really like... I just feel like if I do it... Yeah, wow, cool. Can I do it? Bro, valid Sudoku. Valid Sudoku. Fuck what you talking, valid Sudoku, nigga. Can I try? Can I try? Is me trying? Fucking hell, bro. Fucking dipshits. You gotta pay money. Okay. Let me practice. So we have A and we have B, and we need to add both of them. So addition, just matrix A and matrix B. Just adding the, okay. So solution, user function template use. Okay. Let's see, what do you guys have? So should I go, so for I in this thing, Max. Okay, let's do max. Max of this thing, comma, whichever gets the biggest, z. So what do I need to do? I need to get an output function. I mean output is equal to a 0 matrix multiplied by the length of this thing right here. Should not, yeah, the length. Bro, it's so it's so tiny. So I'm going output is equal to, I need to replace, right? So matrix A. Matrix A is going to be I plus matrix B is going to be I. You need to add both of them and custom and return output. Bro, I just want to see the answer now. Okay. Can this shit be like, okay, bro. Can you guys do it in Python or something? Just saying. They're closely related.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem matrix diagonal sum. Even though this is an easy one, it can be a little tricky to code it up in a pretty concise way. So I'm really going to break down my thought process for you in this problem, and by the end of the video, I really want you to feel like you could have solved this problem by yourself. So we're given a
Okay. Oh. You're given a square matrix. Return the sum of matrix diagonals. Only the sum, only the element. Okay. What the hell? Only include the sum of the elements of the primary diagonal and all the elements of the secondary diagonal, not the part of primary diagonal. Whatever the fuck that means. So diagonal matrices. What even is diagonal matrix? I don't know. I'm only doing this diagonal or this diagonal. I think I'm only doing this diagonal, right? So when I add it up, add that all up, maybe 34. 19, 20, 30, bro, what the fuck? Okay, this 19, 20, 30, 17, 34. That makes complete sense. And here we have 15, 26. What the fuck?
square matrix, and we want to return the
Ooga booga. Asking in AI sometimes it's matrix sheets. Okay, tech interview handbook. Essential questions, set matrix. Okay. Stupid. Why don't you guys just ask what the must know 20 manipulation and traversal, diagram and spiral and all of that bullshit, optimization. Oh my god, I need to learn this. Matrix problem, medium. What the hell? Does it work?
We got a time limit exceeded. We can optimize this further. How we can optimize this? See, every divisor exists.
Nigga, what are you yapping? These niggas yapping, man. Matrix technical interview tutorial. Happy coding. Bro, what am I looking at? Okay, after dynamic programming, I'm gonna sit and do some matrix. Oh, it is in matrix. Of course. Of course. Bro, That was a waste of time. What I did there, right there, waste of time. Count the odd number in interval. Yeah, that was so fucking stupid. Of course, it's in the matrix. Fuck's sake. I think it is useful for me to know this. There is some sort of transferability to other things, which I need to learn this, but I need to master the top triangle before doing this. That's the concern. Okay, now that's out of the way. I'm not gonna learn this now. Should I, bro? It's a completely new language too. And this nigga doesn't have search trees, heaps, sorting techniques.
In this video, I'll give introduction to stack data structure and some of its applications, where it is used and all. Then I'll be discussing abstract data type of stack ADT. Stack is a data structure which works on discipline last in first out. Actually, stack is a collection of elements, set of values, collection of elements. And those collection of elements, they are inserted and deleted by following this discipline. So if you're inserting the elements, then when you want to delete, which one can be deleted? Only the last one that was inserted, that can be deleted first. So this type of mechanism, we use it in our daily life at many places. See, whatever we do manually, we want to automate that one, that is computerize that one. So we write the procedures or the programs for those things. So we want our computers to do that. If we are using a stack in some application, then in our program also, stack will be used there. Let us see a few examples where stack is used in our daily life. So one example, if suppose there is a dead-end lane, and in this lane, cars are parked. Suppose there is a first car, this is a red color car, this is black color car, this is white color car. This is a dead-end lane and 3 cars are parked here. So it means they are brought inside this lane from this direction. Then if I want to take out these cars, from which direction they should go out? This side is closed, so they have to go out from the same direction. So this side of the lane they can go out. So which car was inserted last? Right car. Which car will go out first? White. Times when the recursions are converted into iteration, we have to use stack also. Not every recursion. Some recursions are directly converted to iteration, some recursions we require a stack. So I will discuss this as a separate topic. I will take some examples and show you where the stack is required, where the stack is not required. So we will discuss this as a separate topic. But
okay, I'm kinda lost. Don't know what to do. Maybe I should do sliding window? Probably not. Fuck it, bro. Let's just do trees. Fuck it, we ball.
this section is about trees. So we learn about general trees and binary trees and various types of binary trees. So in this video, we'll learn about the terminology of trees and introduction to binary trees. So let us start with terminology. See, here I have taken a general tree, and nodes are containing alphabet so that it's easy for you to understand. Let us define a tree. Tree is a collection of nodes or what?
Okay, I need to break. What? Okay, I think I did
What is this? And
one lead code, which is fine. A short little fucking 7 hours. The fuck? Yeah, the last one is kind of a drag. Okay, I think what I need is I need to do the trees now because I want to do the linked list. If it's needed, I might do it. So for this time period, I think I'm done with the top tree. I might come back and do the sliding window. Does he have the sliding window? Yeah, he doesn't have the sliding window. Let's see. Let's see if my boy has the sliding window on lock. Yeah, I might do the sliding window coming back. Okay, I'm gonna start with the sliding window first, then I'm gonna go to the trees and go deep on the trees because I need to. So trees, binary search tree, able tree, search tree, and what else? Yeah, I think trees is the next logical thing. I have like 8 hours to think. Okay. Hello. சாப்பிடணும் சாப்பிடணும் நஸ்டேக் செஞ்சு சமைச்சு சாப்பிடுவேன் நஸ்டேக் செஞ்சு சமைச்சுவேன் சாப்பிடுவேன் என்ன இந்தாங்க இந்தாங்க இந்தாங்கம்மா
அது எங்க வந்திருக்கு
எங்க
என்னோடது
Okay, bro. I think I would have been locked in for like 7 hours, but I think I need to keep going. Keep going. What do I need? Let's actually watch this fireship video.
In the beginning, there was nothing. Then someone invented 1, and then someone else invented 0, and everyone said, wow, this is useless. Then about 20,000 years later, electricity shows up. Electricity likes on and off. On is 1, off is 0. Suddenly, we're programming stuff. They say, what if we combine 1 and 0? So they do. 1 0 1 0 1 0 1 0. Nobody knows what it means, but it feels important. 1936 rolls around. This guy defines what computable even means. He goes on to crack the Nazi Enigma machine to save the war for Britain, but he's way too gay, so they throw him in prison. The war is over, and people realize computing machines are pretty useful. They use vacuum tubes and punch cards to represent 1s and 0s. They call each number a bit, or a binary number. It's how computers think. They don't understand words, they understand voltage. And then someone had the idea, what if we take 8 bits to represent a regular number? Everyone agrees, and now we can count to 255. Then this guy says, dudes, let's call this 8-pack of bits a byte with a Y to make it sound futuristic and cool. And now people start arranging 1s and 0s all day to make machines do math, and they realize this sucks. So this woman shows up and says, absolutely not, and invents assembly language. Instead of writing 10110000, you write MOV. It still sucks, but now it sucks less. Then another woman shows up and completely changes everything. Grace says, what if computers could understand something like English? Everyone laughs. They tell her to go make a sandwich. So she does, and calls it a compiler. A compiler is like a translator. You give it readable code, it thinks really hard, then gives you a new file. That file is machine code, a bunch of 1s and 0s again. The computer loves it, you never look at it again. This leads to the first high-level programming languages. Fortran for scientists, COBOL for businesses and government. Somehow, half of global finance still runs on COBOL. No one knows how, no one touches it. Meanwhile, this weird guy creates this weird language called Lisp. Everything is a list. Code is data, data is code. It doesn't even need a compiler. Instead, it uses an as a list, coaches it. Meanwhile, this weird guy creates this finance still runs Fortran for scientists, COBOL for businesses and government. Somehow, half of global finance still runs on COBOL. No one knows how, no one touches it. Meanwhile, this weird guy creates this weird language called Lisp. Everything is a list. Code is data, data is code. It doesn't even need a compiler. Instead, it uses an interpreter that runs code line by line on the fly until the code stops working. Wild stuff, and it also unlocks a new superpower called garbage collection, where the programmer no longer even needs to think about memory. After everyone does LSD in the late 60s, things start to get weird in the early 70s. Dijkstra says go-to statements are trash, and everybody agrees that we need readable, maintainable code. Dennis invents C. C is fast. C is powerful. C lets you shoot yourself in the foot with military precision. But C lets you talk directly to memory, which means power. Dennis has a buddy named Ken. Together, they use C to make Unix. It's an operating system. It's not the first one, but it's the only one that still matters. Instead of one giant machine, we get small programs. They each do one thing well and pipe data to each other, like CD to change directories and LS to list out its contents. The idea infects everything, and now the command line becomes religion among programmers. Everything was perfect, then this guy comes along and says what if C, but with more abstraction. So he adds a plus to it, and then another plus. And now all of a sudden, we have objects, classes, inheritance, and arguments that never end. Programmers love complexity, so C++ takes over the world. Games, browsers, databases, engines are all built with C++ even today, and people still can't stop arguing about it. Now the year is 1982. Every nerd owns a Commodore 64 while learning how to code in BASIC, while the year is 1982. Every nerd owns a Commodore 64 while learning how to code in BASIC while listening to Thriller on a record player. Soon, Turbo Pascal shows up. Like C, it has a compiler, but also a full integrated development environment. It sells like Thriller, but many new programming languages are hitting the scene. Ada is created for the military, Erlang for the phone system, MATLAB, Perl, Objective-C, and more. Oh, and don't forget Smalltalk, one of the first pure object-oriented languages where everything is an object. Everybody forgets about it, but everybody copies it. Then the 90s happen, and three philosophies collide. Guido says code should read like thoughts, so we get Python, where readability matters and indentation is law. But James says programs should run everywhere, so we get Java, where you write once and debug everywhere. Java doesn't just ship a language, but also a revolutionary virtual machine, which is like a fake computer that runs in the real computer and compiles Java to bytecode instead of machine code. It's basically
burger bun இருக்கு வச்சு கூட சாப்பிட்டுக்கலாம். சீஸ் உள்ள இருக்கு.
cheating to get Java to run everywhere. But then Brendan comes along and invents JavaScript in 10 days to make buttons animate in the browser. It was supposed to be small, it was supposed to be temporary. It now runs servers, phones, databases, and spacecraft. No one planned this, no one wanted this. Then the World Wide Web happened. The experts said it would be no more important than the fax machine. But billions of websites were created anyway, most of them with PHP. Nobody likes to talk about PHP, only JavaScript frameworks. Wars were fought over JavaScript frameworks like jQuery, MooTools, React, Angular, Vue, Svelte, and thousands more. Many people died from unrelated causes, but they didn't die for nothing. Throughout the 2000s, languages became cleaner and more elegant. Swift fixed Objective-C, Kotlin fixed Java, TypeScript fixed JavaScript, Go fixed C, Rust fixed C, no, Zig fixed C, JK, C is still the best. In 2020, the world is beautiful and perfect. Programmers are cool, programmers are rich, and programmers are highly desirable mates. Even Fireship was making good videos without any AI slop. But then the asteroid hit. Someone says, what if we can get statistics to write code? First it's autocomplete, then linters, then refactors, then whole functions, then entire full stack applications. And suddenly everybody says programming is dead. But here's the secret. Typing code was never the job. The job was thinking. Thinking with your brain. Programming isn't dead, it just keeps changing the keyboard, and it always will. And one tool that's changed the way I use the keyboard comes from JetBrains, the sponsor of today's video. Their AI
I would really like to eat. I think offline I'm gonna watch some videos. Okay. I think I'm done. It's been an eventful day. That's my stream. So I think I will be signing off.